AlphaZero is a game-playing algorithm that uses artificial intelligence and machine learning techniques to learn to play board games at superhuman levels. In this machine learning course from Robert Förster, you will learn how to create AlphaZero from scratch.
Thank you for tuning in. In this video, we are going to rebuild AlphaZero completely from scratch using Python and the deep learning framework PyTorch. AlphaZero was initially developed by DeepMind, and it is able to achieve magnificent performance in extremely complex board games, such as Go, where the amount of legal board positions is actually significantly higher than the amount of atoms that are in our universe. So not only is this very impressive just from an AI standpoint on, but additionally to that, the machine learning system of AlphaZero learns all of this information just by playing with itself. And moreover, the various domains in which this algorithm can be used are almost limitless. So not only can this algorithm also play chess and shogi in a very impressive way, but the recent AlphaTensor paper that was also published by DeepMind showed that AlphaZero can even be used to invent novel algorithms inside of mathematics. So together, we will first of all understand how this algorithm works, and then we will build it from ground up and train and evaluate it on the games of TicTacToe and ConnectFour, so that you will also understand how flexible AlphaZero really is when it comes to adapting it to various domains. So let's get started. Okay, great. So let's start with a brief overview of the AlphaZero algorithm. So first of all, it is important that we have two separate components. And on one hand, we have the self-play part right here. And during this phase, our AlphaZero model basically plays with itself in order to gather some information about the game. And while we play with ourselves, we also generate data, and this data will then be used in the next step during training. So in this training phase right here, which is the second component, we like to optimize our model based on the information it gained while playing with itself. And then next, we basically want to fulfill the cycle and then use this optimized model to play with itself again. So the idea is essentially to repeat the cycle n number of times until we have reached a neural network, so a model right here, that is capable of playing a certain game better than any human could, because it just played with itself, used the information it gained to optimize itself, and then play with itself again, basically. And then we just like to repeat that. So in between these two components, we have this AlphaZero model right here, which is just a neural network. And now let's look at this neural network more closely. So let's see how this actually is architectured. So basically we take the state S here as input. And for the case of TicTacToe, for example, the state would just be board position. So just turn two numbers. And then once we have the state here as input, we receive a policy and a value as output. So the policy here is this distribution. And for each action, basically it will tell us how promising this action would be based on this state we have received here as input. So it will basically tell us where to play based on this state right here. So this is the policy. And then the value is just a float, and it will basically be a measure telling us how promising the state itself is for us as a player to be in. So maybe a concrete example that might make all of this easier to understand is something we have down below here. So here for the state, we just take in this position, and remember that we are player X in this case. And if you're familiar with the rules of TicTacToe, you should see that we should play down here, because then we would have 3 X's on the lowest row, and we would win the game. So if our model also understands how to play this game, then we would like to receive a policy looking somewhat like this, where basically the highest bar right here is also this position down below. That would basically help us to win the game. So yeah, this is how the policies should look like. And for the value, we can see that this state is quite nice for us as a player because we can win here. So we would like to have a very high value. So yeah, in this case, the value is just a float in the range of -1 and +1. So we would like to have a value that is close to +1 because this state is quite optimal. Okay, now we looked at how the general architecture is built and how the model is built. But next we want to understand the self-play and the training part more in depth. So before we do that, you should also understand what a Monte Carlo tree search is, because that is vital for self-play and the general algorithm. So the Monte Carlo tree search is this search algorithm right here. And it will take a state, or in our case, a board position as input. And then it will find the action that looked most promising to us. And this algorithm gets this information by just, first of all, declaring a root node at the initial state right here. And then by building up this tree into the future. So just like we can see right here. So basically the idea is that we create these nodes into the future right here. And we get these nodes by just taking actions that lead us to the future. So this node right here, for example, is just the place we arrive at when we take this action 1 based on this initial state at our root node. So each node, first of all, stores a state, like S1 in this case. And so S3 right here would just be the state we get when we first of all play action 1 based on this initial state, and then when we would play action 3 based on this state right here. So playing these actions after each other, basically. And then additionally to the state, each node also stores this variable W. And W is just the total number of wins that we achieved when we played in this direction into the future. So basically when we took action 1 initially and arrived at this node, we were able to win 3 times when we walked into the future even further. So next to this variable, we also have this N variable right here. And N is just the total visit count. So basically the total number of times that we went into this direction. So here we can say that we took action 1 4 times. And out of these 4 times, we were able to win 3 times, right? So after we have basically built up a tree like this, we can then find the action that looks most promising to us. And the way we do this is by looking at the children of our root node. So these 2 nodes right here. And then for each node, we can calculate the winning ratio. So here we can say that this node won 3 out of 4 times, while this node won 1 out of 2 times. And then we can say that, you know what, this node right here has a higher winning ratio, and thus it looks more promising to us. And because of that, we can also say that action 1 looks more promising than action 2, because this action was the one that even led us to this node here in the first place. So basically the result of this tree right here that we got at this time would be that action 1 should be the action we would like to play. And then we could just use this information to say, you know what, in our actual game of TicTacToe, for example, we now want to use this action right here. So this is great, but now the question becomes, how can we even build up a tree like this? And also, how do we get the information whether we win at this given position or not, right? So the way we come up with all of this data right here is basically by walking down all of these 4 steps for a given number of iterations. So at the beginning, we are in our selection phase, and during selection, we basically walk down our tree. But we walk down our tree until we have reached a so-called leaf node. So a leaf node is a node that could be expanded even further. into the future. So one example of a leaf node would be this node right here, because you can see that we have only one child as this node, but actually we could also expand in this direction. If we say that for each node, there are always two possible ways in which you could expand in this example right here. So this is a leaf node. And then also this would be a leaf node right here, because this node doesn't have any child, right? And then also we can say that this node also is a leaf node because it only has one child right here, but we could still expand it in this direction. So yeah, these are leaf nodes, for example, while these aren't any leaf nodes because this one already has two children and this one also has two children already. So yeah, this is basically how selection looks like. But now the question also becomes, when we walk down, which direction we should pick, right? So when we just start at the top, we now have to decide whether we want to walk down in this direction or whether we want to walk down in this direction right here. Basically, the way of finding out the direction we choose when walking down is by taking the direction or the child right here that has the highest UCB formula like this. So while this might look a bit complex, in reality, we just take the child that tends to win more often, while also trying to take a child that has been visited just a few number of times relatively, right? So on one hand, when we maximize this formula, we want to take the child with the highest winning ratio, and also want to take the child that has relatively few visits compared to this large N, which is just the total number of visits for the parent. So if we would calculate the UCB formula for both of these nodes right here, we can see that the UCB formula here is higher because this node has been visited less often, right? And because of that, we would like to walk in this direction right here. Okay, so during selection, we can now say that we walk down in this direction right here. And now we have arrived at this node. So first of all, we have to check if we walk down further or if we have in fact reached a leaf node. And now we can see that we have reached a leaf node right here, right? Because we could still expand in this direction. So we could still have a child right here. And because of that, we actually skip to the next phase of the MCTS, and that is the expansion phase. So right here, in expansion, we want to create a new node and append it to our tree. So I will just create this node right here, and I will call it, give it the state as 7. Then we can say that we took the action A7 to get to this newly created node right here. And at the beginning, this node should have a winning count of 0 and also a visit count of 0. So I'm just going to declare W7 right here and also N7 like this. And both of them should just be equal to 0 at the beginning, right? Because we have just created this node and added it to our tree, but we have never been there actually. So now we can say that we further walk down here to the node we have just created. And so now we have also finished this expansion phase right here. And next, we have arrived at this simulation phase. And here the idea is basically to play randomly into the future until we have reached a state where the game is over, right? So we want to play into the future until the game is finished. And basically here we can just say we play using random actions. So we just play randomly. And finally, we have just reached this node right here. And here the game is over. So this is the simulation phase. And now when we have reached this terminal node, basically, we then have to check whether we have won the game or we have lost or a draw has occurred. So in this concrete case, we actually have won. And with that, we can also finish the simulation phase. So just finally now, we have arrived at the backpropagation phase. And here we like to get this information from our simulation. And then we want to give this information all the way up to our parents until we have reached the root node. So here, because we have won the game actually, during backpropagation, we can first of all higher the number of wins for this node right here. So we can say that we have won one time actually. Then we can also higher the total number of visits. So here we have visited this node one time and we have won in this case. And because we want to backpropagate all the way up, we can now also say that here for this node, the number of wins now is 2. So the number of wins we got when we walked in this direction, right? And then also the total number of visits should now be 3 because we have visited it when we selected inside in this direction. And now we can also backpropagate all the way to our root node. And here we can just say that the general visit count is 7 and the total number of wins would be 5, right? Okay. So now this would be a whole iteration of this MCTS process. And then if we would again choose an action, we would just check the children of our root again, and again could just choose the action based on the winning amount of wins right here. So this is great. Let's also just have an example where we start from all the beginning, so that you might find it easier to understand the search algorithm as well. So again, we want to perform these steps right here. So at the beginning, we are just in our selection phase. So we want to walk down until we have reached the leaf node. But here you can see that this root node already is a leaf node, right? So basically we can now move on to expansion and create a new node right here. So let's say that we just create this node right here by taking action 1. And then we will arrive at state 1 here as well. And then we can say that at this node that we have just created, the total number of wins right now should just be 0. And also the visit count should just be 0. So we have W1 and N1 just created right here. And both of them can just equal 0 like this. So now we have also finished the expansion part for the first iteration. And next comes the simulation part, right? So we have walked this way basically right here. And now we want to simulate into the future just by taking these random actions. So let's write this right here. And now we have reached a terminal node. And now we have to check whether we have won or lost or a draw has occurred again. So in this case, we can just say that we have won again. So because of that, we actually can backpropagate now. And in backpropagation, we can say that the number of wins here is 1, with the visit count being 1 as well. And then we can do the same for our root node right here. So we can just say that the number of wins for our root node is also 1. And the visit count of our root node is also 1 as well. So now that we are finished with this iteration, I'm just going to clean everything up here. And we can move on to the next iteration, right? So again, we start at selection and we walk down until we have reached the leaf node. But again, we can see that our root node actually still is a leaf node. So let's just expand this direction now. And here we will just use action 2 and we will arrive at state 2. And here again, we have to set the total number of wins to 0. So W2 should be equal to 0. Sorry, this also S2. And then the visit count, so N2 should also equal 0 right here. So let's write n2 equals 0 as well. So let's do it like this. And yeah, now basically we walk in this direction right here. And next we can do simulation again. So let's simulate all the way down until we have reached the terminal node. And in this case, we can say that we have actually lost the game. So when I backpropagate all the way up, I will only increase the visit count right here. So the visit count should now be 1, but the total number of wins should still stay the same, being 0, because we have lost here when we simulated. So because of that, when we backpropagate to our root node, we should also only increase the visit count while leaving the total number of wins the way it was earlier. So let's also finish up with this iteration right here. And now we can move on to the next iteration. So first of all, we want to do selection again. So we want to walk down until we have reached the leaf node. And now our root node is fully expanded. So we have to calculate the UCB score for each of our children right here. And then we have to select the child that has the highest UCB score, right? So when we calculate the UCB score for both of them, we can see that the UCB score here is higher because we have won the game in this case. So we just walk down in this direction right here. And now, basically we can move on to expansion. So let's expand in this direction here. So let's create this new node right here and append it to our tree. And we took action 3 actually when we expanded in this direction. And then the state here should also be S3 because of that. And now again, we can declare this total number of wins W, so W3, and the visit count N3. And both of them should just equal 0 at the beginning. So let's set them to 0. And now again, we can perform this, basically can perform simulation again. So we walk down in this direction right here. And yeah. So now let's do simulation. And when we do that, we just arrive at this terminal node again. And again, we can now see that in this case, we have just lost the game after just playing randomly. And because of that, when we backpropagate, we only want to increase the visit count right here while not changing the total number of wins. So let's set the visit count to 2 here as well. And then we can set the visit count to 3 here. Okay. So this is this iteration right here. Great. So now we can just also clean all of this up right here. And then we can move on. So next, when we want to keep doing this process right here, we again have to do selection, right? So now we have to again calculate the UCB formula for both of these values right here. And here we can see that the UCB formula actually gives us a higher result for this node, just because of the visit count that is lower right here. So when we now walk in this direction, we again have to check if we have reached the leaf node or not. So here we have just reached the leaf node. So because of that, we move to expansion and create this new node right here. And this should just be equal to S4 then. So we can say that we took action 4 right here. And then again, the W and the visit count should be set to 0. sorry, one color. So W4 and N4 here being our number of wins and our visit count. And let's set them to 0 like this. Okay. So now we also walk in this direction right here. And again, after expansion, we can now move to simulation. So when we move here, the game is terminal. And in this case, we can just say that a draw has occurred. And you know what? In case of a draw, we just would like to add 0.5 to the total number of wins, because no player has won here, or no one has won. So because of that, when we backpropagate here, first of all, we can increase the visit count. And then let's set the number of wins to 0.5. And then up here, we can set the visit count to 2. And again, the total number of wins should be 0.5. And when we backpropagate all the way up to our root node, then we have the total number of visits as being 4. And our total number of wins should be 1.5. So this is just an example of how the Monte Carlo tree search might actually look when you just start at the beginning. And actually you can repeat this cycle for just a set number of iterations. And you set this number manually at the beginning. And alternatively, you could also set a time. And during this time, you would just perform as many iterations as you can. But yeah, in this case, for example, you could just stop at 4 iterations, but in practice, you might run for thousands of iterations. Okay, so now we can also look at the way how our Monte Carlo tree search changes when we adapt it to this general AlphaZero algorithm. So there are 2 key changes that have been made here. So the first thing is that we also want to incorporate the policy that was gained from our model into the search process, right? And especially we want to add it to the selection phase right here. And we can do this by incorporating it into this updated UCB formula. So this way you see this P of I part right here. So basically when we select a child and we want to take the children with the highest UCB formula, then we will also look at the policy that was assigned to it from its parent perspective. So remember that the policy is just this distribution of likelihoods. And basically for each child, when we expand it, we will also store this policy likelihood at the given position here for the node as well. And because of that, we then also tend to select children more often that were assigned a high policy by its parent, right? So this way our model can guide us through the selection phase inside of our Monte Carlo tree search. So yeah, this is the first key change here. So just generally this updated UCB formula right here. And then for the next change, we also want to use the information of the value that we got from our neural network. And we can use this information by, first of all, completely getting rid of this simulation phase, right here. So we don't want to do these random rollouts into the future anymore until we have reached a terminal state, but rather we will just use the value that we got from our neural network when it basically evaluated a certain state. And this value will then be used for backpropagation, right? So this way we use both the policy for our selection and the value for our backpropagation of our neural network. And because of that, we know that our Monte Carlo tree search will improve drastically when we also have a model that understands how to play the game. So this way, at the end, we then have a better search with a better model that we can even create a much better model, right? So we can keep the cycle up this way. Okay, so there's also just a small change here as well, just a minor one. And remember that when we get the policy from our neural network, we immediately get this distribution, right, with the probabilities for each potential child. And because of that, it's much more convenient now to expand in all possible directions during the expansion phase. So we won't only create one new node, but rather all of the possible nodes that we can expand on, right? So this is just a minor change. And so in order to make this easier to understand, we can just do some iterations here on the whiteboard together. So yeah, this way it might be easier to fully understand how this Monte Carlo tree search is adapted. So first, you might also see here that we also store this policy information here inside of our node. And yeah, this will just be the probability that was assigned to it from its parent, right? And for the root node, we just have no policy probability because we also have no parent. But for other nodes, we will also store this policy here inside of our node. Okay, so let's start with an iteration here. So first of all, we want to walk down until we have reached the leaf node. And here we can already see that our root node is in fact a leaf node because we can still expand it in these two directions here. So because of that, we will then move to the next step right here, which is the expansion phase. And here we will actually create our new nodes. So now when we expand, we also want to get a policy and a value from our neural network. So because of that, I will first of all write P, and then value equals, just calling our neural network at the state of our root node. And let's say this policy right here will just be 0.6 for the first child, and then maybe 0.4 for the second child. And let's say that this value, so the estimation of how good this state of our root node is just 0.4 here. Okay, so now when we expand, we will create these two new nodes right here. So these two. And here we have action 1, right? And here we have action 2. So because of that, we also have state 1 here, and we have state 2 right here. So now we can also add the number of wins, the visit count, and the policy information to our nodes right here. So first of all, I will create this W1 and set that equal to 0. Then I will create this N1 and set that also equal to 0. And now we have this policy probability 1. And this should be equal to the policy for action 1. And here the policy for action 1 is just 0.6. So yeah, the policy here should be 0.6 because of that. So now we can also add the information here to the other child. So let's first of all set the number of wins or the value later on here to 0 as well for W2. And let's set N2 to 0 as well. And the policy probability for this child right here should now be equal to 0.4, right? Like this. Okay, so now we have expanded here and we skip this step here. So now we move to the backpropagation step. And here we just want to backpropagate this value right here. So we will just do this by just adding it right here. So basically, in this case, it doesn't matter much for our root node, but maybe it's some nice information. So we can just add 0.4 here, and then because of that, also change the visit count to 1, right? Okay, so this was one iteration, and now we can move on to the next iteration. So I will just clean this up. Okay, so now again, we want to walk down until we reach a leaf node. So now we have to decide between those two children, right? And for each, we have to calculate the UCB formula, and then also we will just walk down in the direction where the UCB formula is the highest, right? So when we calculate this UCB formula, we will see that no longer can we basically get the winning winning probability here, because we have a visit count that is equal to 0. So currently, the way this is implemented, we would get a division by 0 error. So here we have to make sure that we will only check for the winning probability if we have a visit count that is larger than 0. So because of that, I will just set that in brackets right here. So we will only check for this if we have a visit count that is larger than 0. And in all other cases, we will just mask it out. So we will just check for this part right here. Okay. So now we can find out the child where this value is the highest. And we can see that we will just pick this child right here because it has the higher policy probability. And because of that, its UCB formula will also be higher. So because of that, we will just walk in this direction right here. So now we have reached a leaf node here, and we would like to expand this node here. So let's expand in these two directions. So first of all, this should be action 3, and this should be action 4 right here. So when we create these new states, we have state 3, and we have state 4 like this. Okay, so now, again, we also have to calculate a new policy and a new value. So we will get this policy and this value by calling our neural network F with this state here, so S1, because this is the position we have walked down to. And from here, we want to find out what the policy would be for these children, and also what the value would be for this node directly. So let's say that the policy here is just 0.5 and 0.5 for both. And let's say that this value right here is just 0.1. So now, first of all, we can also add this information here to our nodes again. So let's first of all set W4 equal to 0. Then we can set N4 equal to 0. And then policy probability 4 should be equal to 0.5. And then here we also have W3, which should just be 0. And we have N3, which should also be 0. And then we have also our policy probability 3 here, and this should be equal to 0.5. I hope you can read that here. Okay, so now we have expanded these two children right here, and created them and stored the policy information here inside of them. So now we want to backpropagate again. So here we will just use this value of 0.1. So actually we will add 0.1 here, and we will raise this visit count by 1. So let's change that 1 right here. And remember that we want to backpropagate all the way up to our root node. So here we will change the value, so W0 here, to 0.5. So also add 0.1 to it. And then we will just raise this number of visit counts by 1 as well. So it will be 2 afterwards. So this is just this updated tree after just 2 iterations. But again, if we would repeat this, we would just first of all walk down until we have reached a leaf node. Then we would expand and use the policy here when we store the policy information in the new children. And then we would just use the value for backpropagating up all the way in our tree to our root node, right? So these are just the small changes that have been added to our Monte Carlo tree search. Great. So now that you know what a Monte Carlo tree search is and how we adapt our Monte Carlo tree search during our AlphaZero algorithm, we can actually move to the self-play part right here. So basically during self-play, we just play games with ourselves from the beginning to end. And so we start by just getting this initial state right here with this, which is just a completely blank state. And we also are assigned to a player. And then based on this state player position, we perform a Monte Carlo tree search. And yeah, this multi-color tree search will then give us this distribution as a return, which is equal to the visit count distribution of the children of our root node, right? And once we have this distribution, we then would like to sample an action out of this distribution. So in this case right here, we, for example, sampled this action, which is highlighted here because, yeah, it turned out to be quite promising during our multicolored tree search. So once we have sampled this action, we want to act based on it. So we play here, basically as player X. And then, yeah, we move to the next state. And we also switch the player around so that we are now player circle or player O. And we have this state basically as input at the beginning. And then again, we want to perform this multicolored tree search right here. And we gain this MCTS distribution. Then we just sample one action out of it. We play based on this action. And then we can basically change the perspective again so that we are now player X. And we basically continuously perform a multicolored tree search, sample an action out of it, play this action right here, and then change the perspective so that we are now the other player or the opponent. And we do that until we actually have reached a terminated state. So once a player has won or a draw has occurred. And yeah, so when this is the case, we want to store all of this information we gained while playing to the training data. So let's first of all look how this information is structured. So basically for each state, we also want to store the MCTS distribution. And then we also need to find out the reward for the given state. The reward is equal to the final outcome for the player that we are on this given state. So basically in this example right here, X won the game. So that means that for all states when we were player X, we want the final reward or final outcome be equal to 1. And in all cases when we were player O, we want the reward to be -1 because we lost the game. So basically that means that, you know what, we won this game as player X right here. So we might just guess that this state also is quite promising because, yeah, this state led us to win the game eventually. So this is why we change this reward to +1 here when we are player X. And this is also the reason why we change the reward to -1 when we are player O here. So these combinations of the state, the MCTS distribution, and the reward will then be stored as tuples to our training data. And then we can later use these for training, right? In order to improve our model. So this is great, but now we have to understand how training works. So yeah, let's look at this right here. So at the beginning, we just take a sample from our training data. And yeah, you should know now that this sample is the state, the MCTS distribution, and pi, and the reward z right here. And then we will use the state s as the input for our model. Then we will get this policy and this value out as a return. And now for training, the next step basically is to minimize the difference between the policy p and the MCTS distribution at the given state pi on one hand. And then we also want to minimize the difference of our value v here and the final reward or final outcome z we sampled from our training data. And the way we can minimize the difference basically in a loss is first of all by having a mean squared error between the reward and the value here. And then by also having this multi-target cross entropy loss between our MCTS distribution pi and our policy p right here. And then we also have some form of L2 regularization at the end, but yeah, so essentially we want to have this loss right here. And then we want to minimize the loss by backpropagation. And this way we actually update the weights of our model, theta, right here. And we also thus get a model that better understands how to play the game and that has been optimized. And then we can use this optimized model to again play with itself in order to gain more information, in order to train again, and so on, right? So this is how AlphaZero is structured. And now we can actually get to coding. So let's actually start by programming AlphaZero. So first of all, we're going to build everything inside of a Jupyter notebook, since the interactivity might be nice for understanding the algorithm. And also this might help you if you want to use Google Colab, for example, to use Google's GPUs to train AlphaZero more efficiently. And we will start everything just by creating a simple game of TicTacToe. And then we will build a Monte Carlo tree search around it. And after we have gone so far, we will eventually build AlphaZero on top of the Monte Carlo tree search we had previously. And then we will expand our portfolio to ConnectFour as well. And not only should this be easier to understand, but it should also show how flexible AlphaZero really is when it comes to solving different environments or board games in this case. So for TicTacToe, we want to use NumPy as a package. So I will just import NumPy SNP right here. And if you are wondering, my version currently is this right here. So let's just create a class of TicTacToe and a simple init. And we first of all want to have a row count, which equals 3. A column count as well, should also be 3. And then we also need an action size. And the action size is just the amount of rows multiplied with the amount of columns. So self.row count times self.column count. So that's great. And now we can write a method to get our initial state. So this is what we will call at the beginning. And at the beginning, the state is just full of zeros, so we will just return np.zeros. And the shape here is the row count for the number of rows and the column count for the number of columns. And next, we also want a method that will give us the next state after action has been taken. So we write get next state here, and as input we want the previous state, the action, and also the player. So the action itself will be just an integer between 0 and 8, where 0 will be the corner up left and 8 will be the corner down right. So actually we want to encode this action into a row and a column so that we can use it inside of our NumPy array. So the way we do this is that we define the row as the action divided by the column count, but we'll use an integer division here, so we will get no floats. And then for the column, we can use the modulo of the action and the column count as well. So if our action would be 4, for example, then our row would be a 4 integer division by 3, which would just return 1. And our column would be 4 modulo 3, which is also 1. So we would have row 1 and then column 1 as well. So the middle of our board, which is exactly what we want. So then we can set the state at the row, at the given column, to the player we had as input. And let's also return the state, so our code is more readable. So that's awesome. And next we also want a method that will tell us what moves are actually legal. So these are just the moves where the field is equal to 0. So let's write a method getValidMoves. And also give a status input, and then we can just return state.reshape -1, so we flatten out the state, and then we can check if the state is equal to 0. And this will give us a Boolean array back, so true or false, but it's quite helpful if we have integers here. So I will turn the type to np.uint8, so unsigned integers. And yeah, that's awesome. So now we also want a method that will tell us if a player has won after he he acted in a certain way. So let's also write a method for that. So just def check win. And here we want a state and an action. So let us first get the row again. So we just say action integer division self.column count. And let's also get the column here. Nice. So now we can also get the player that played in the given position. And the way we do this is just that we check the state at the row and the column. So basically we turn this expression here in the other way around. And actually in TicTacToe, there are 4 different ways in which you could win a game. So first of all, you could have 3 in a row like this, or you could have 3 in a column like this, or 3 in this diagonal, or 3 in this diagonal right here. And we want to check for all of these 4 conditions. And if one of them turns out to be true, then we will return true as well. And none of them are true, then we just return false. So let's write out all of these expressions right here. So first of all, we can just check if there are 3 in a row. So we will use np.sum of the state of the given row and all of the columns inside of that row. And we want to check if that sum right here is equal to the player times the column count. Yeah. And then we can also check whether there are 3 in a column like this. So we just use np.sum of state of all of the rows for a given column. And then again, we check if that equals player times self.column count. Oh, row count in this case. I mean, let's be more flexible here. And that's great. So now we want to check for this diagonal. And the way we can do this is by using the np.diag method. So I put up the documentation right here. And if we would have an array like this, which we also want to have for TicTacToe, then we can use this diag method right here to get the values from this diagonal. So let's use this to also check if someone has won. So we use np.sum of np.diag of state. And we'll check if that's equal to player times self.row count or self.column count. In this case, it doesn't matter because you can only get this full diagonal if row count and column count is the same. And next, we also want to get this opposite diagonal right here. And there is no way to do it with the normal diag method, but we can just flip our state and then use this old diag method again. And since our state is flipped, it would be as if our diag itself is flipped, if that makes sense. So we can just use our np.sum of np.diag of np.flip of the state. Let's just say x is equal to 0, so we flip like this. And then we can take the opposite diag, which is what we want. So I'll also check if that equals player times self.row count. So awesome. And next we also want to check if there has been a draw. So if the game terminated in any other way, since this might also be a scenario where we want to stop the game. So let's just write a new method, get value and terminate it. And we want a state and an action. And first of all, we will check if check win is true. In this case, so if check win or self.check win of state of action, then we'll just return 1 for the value and true for terminated. And then we can also check if there has been a draw. And that we know that there has been a draw if the amount of valid moves is 0. So we can just take the sum of the valid moves and check if that's 0. So I say if np.sum of self.getValidMoves of the given state equals 0, then we just return 0 for the value, since no one has won the game, and we will also return true for terminated. And in all other cases, the game must continue, so let's just return 0 and false. Awesome. So now we got a working game of TicTacToe, and additionally would also want to write a method to change the player, since that might be different for different board games. So let's just write a method getOpponent, and yeah, take a player's input, and then we'll just return the negative player. So if our initial player would be -1, we would return 1, and if our initial player would be 1, then we would just return -1. So that's great. And now we can test our game we built right here. So I just say TicTacToe equals TicTacToe. Then I just say player equals 1, and I say state equals TicTacToe dot get initial state. Awesome. So then let's just build while loops. So just say while true. We'll print the state right here. Then we want to get our valid moves, so we know where to play. So I just say valid moves equals TicTacToe dot get valid moves of the state we have currently. And we can also print that. So I just say valid moves. And you know what? Let's print the valid moves in a more readable form, since currently we only have 0s and 1s, but we actually want to get the position where we can play. So I just create this array right here, and I say E for E in range. And then we can just say TicTacToe.ActionSize. So currently we get all the indices for the possible actions. And then we want to check if the indice itself is valid. So we say if valid moves of I equals 1, right? So we want to get all of these indices. And these can just be printed out like this. And then we want to get an action. So the action will just be an input that will be casted to an integer. And let's just write out the player like this. And get the action right here. So then we want to check if the action is valid. So we'll say if valid moves of action equals 0, then we'll just say print action not valid, and we will continue. So we'll ask again, basically. And in all other cases, we want to move. So we'll get a new state, and the new state will be created by calling TicTacToe.getNextState. And we want to give the old state the action and the player's input. Great. So then we can check if the game has been terminated. So we'll just say value is terminal equals TicTacToe.get value and terminated. And then we want to give the state and the action as input. And then we'll say if is terminal, print the state so we know where we are. And then we will check if value equals 1. And then we'll say player has 1. So just say player. So 1 or -1 for the player. And in all other cases, we can just print that there has been a draw. Great. And then we also want to break our while loop, so we can end the game. And in all other cases, if the game continues, we also want to flip the player. So we just say player equals TicTacToe.get opponent of player. So nice, this should be working. So let's test this out. So here are the valid moves. So it's looking nice. So let's just pick 0 for starters. Let's see, nice, okay, we played here. So we are player -1 now, so let's just play 4. At player 0, we can just say 8. Player -1, 1, for example. Player 0, let's say 2. And player -1, we can just say 7. And nice, we see here we got 3 -1s inside of this column right here. And thus we get the result that player -1 has won. Perfect. So now, since we have got our game of tic-tac-toe ready, we can actually build the Monte Carlo tree search around it. So let's just create a new cell right here. And then we want to have a class for our Monte Carlo tree search. So I'm just going to call that MCTS for now. And then we have our init here. And we want to pass on a game, so tic-tac-toe in this case, and then also some arguments. So these are just hyperparameters for our Monte Carlo tree search. So inside of our init, we can say self.game equals game and self.args equals args. And then below we'll define our search method. And this is what we'll actually call when we want to get our MCTS distribution back. So let's just write def search. And for the search, we want to pass a state as input. And inside here, first of all, we'd like to define a root node. And then we want to do all of our search iterations. So for now, we can write for search in range of self.args num searches. And then for each search, we'd like to do the selection phase, then the expansion phase, then the simulation phase, and then the backpropagation phase. And then after we have done all of these things for the given number of searches, we just want to return the visit count distribution. And it's the distribution of visit counts for the children of our root node. So let's just say return visit counts. Yeah, at the end. Yeah, so that's the structure we have inside of our Monte Carlo tree search. And next we can actually define a class for a node as well. So let's write class node here, and then have our init again. And first of all, we'd like to pass on the game and the arguments from the MCTS itself. And then also we want to have a state as a node, and then a parent. But not all nodes have parents. So for the root node, we can just write none here as a placeholder. And then we also want to have an action taken, but again, we have a placeholder of none for the root node here as well. So inside of our init, we can just say self.game equals game, self.args equals args, self.state will equal state, and then again, self.parent equals parent, and self.actionTaken equals actionTaken. So next, we also want to store the children inside of our node. So let's write self.children equals just an empty list. So these are the children of our node. And then also we want to know in which ways we could further expand our node. So for example, if the root node would just be an initial state, then we could expand in all 9 fields for a tic-tac-toe board. And we want to store this information here. So let's just say self.expandable moves equals game.get valid moves of state at the beginning. Then as we keep expanding here, we will also remove these expandable states from our list here. And additionally to all of these attributes, we also want to store the visit count and the value sum of our nodes so that we can later perform our UCB method and get the distribution back at the end. So let's say self.visitCount equals 0 at the beginning, and self.valueSum should also equal 0 when we start. So yeah, that's just the backbone or the beginning structure of our node. And now we can define our root node here. So let's say root equals node, and we have self.game, self.args, and then the state we took here as input. And yeah, parent and action can just stay none. And then inside of our search, we just want to say node equals root at the beginning. And next we want to do selection. So from the video, you might remember that we want to keep selecting downwards the tree as long as our nodes are fully expanded themselves. So for doing so, we should write a method here that will tell us. So def is fully expanded. And a node is fully expanded if there are no expandable moves. So that makes sense. And also if there are children, right? So if our node would be terminated, you obviously can't select past it because the game has ended already. So let's say return np.sum of self.expandable moves. And that should be 0, right? And len of self.children should be larger than 0. So this way we can check whether a node is fully expanded or not. So during our selection phase, we can just say while node is fully expanded. And here we just want to select downwards. We say node equals node.select. So now we can clear this right here. And next we want to write a method that will actually select down. So I'm going to write that here. And the way selection works is that we will loop over all of our children as a node. And for each child, we will calculate the UCB score. And then additionally, at the end, we will just pick the child that has the highest UCB score. So for the beginning, we can just write best child equals none, since we haven't checked any of our children yet. And then best UCB should just be negative mp.infinity. And then we can write for child in self.children. And then UCB equals self.get UCB of this child right here. And then we can check if UCB is larger than best UCB. And if that is the case, we say best child should be child. And best UCB should also equal UCB now, right? And at the end, we can just return best child here. So next we should actually write this method right here we use for calculating the UCB score. And yeah, we want to take a child here as input. And for the UCB score, we first of all have our Q value. And the Q value should be the likelihood of winning for a given node. And then at the end, we have our C, which is a constant that will tell us whether we want to focus on exploration or exploitation. And then at the end, we have a math square root, and then we have a log at the top with the visit count of the parent. And then below, we have the visit count of the child. So we want to, first of all, select nodes that are promising from the win likelihood perceived by the parent. And then also we want to select nodes that haven't been visited that often compared to the total number of visits. So first of all, we should define the Q value. And that should generally be the visit sum of our child divided by its visit count. Its value sum. So the value sum of our child divided by its visit count. And the way we implemented our game would actually be possible to have the negative value sum. And generally, we would like our Q value to be in between the range of 0 and 1, because then we could turn it into a probability. So currently it's between -1 and +1, so let's just add a 1 here. And then at the end we can also divide everything up by 2. And now there's just one more thing we should think about. And that is that actually the Q value right here is what the child thinks of itself, and not how it should be perceived as by the parent. Because you should know that in TicTacToe, the child and the parent generally are different players. So as a parent, we would like to select a child that itself has a very negative or very low value, because as a player, we would like to put our opponent in a bad situation, essentially, right? So we want to switch this around. And we do this by saying 1 minus our old Q value here. So if our child has a now normalized value that is close to 0, then as a parent, this actually should give us a Q value that is almost 1, because this is very good for us to walk down the tree in a way that our child is in a bad position. So now we can just return our UCB right here. So I'm just going to write Q value plus self.args of C. And then that should be multiplicated with math.square root. And we should also import math up here so that we, not like that. So that we can use it. And inside of our square root, we have math.log. And here we have the visit count as a node ourselves. So just self.visitCount. And then we can divide everything up by child.visitCount. Yeah, so that should be it. Perfect. So now we actually have a working selection method here. And now we can move on. So now we have moved down all the tree, selected down the tree as far as we could go, and we have reached a leaf node, or a node that is a terminal one. So before we would like to expand our leaf node, we still have to check whether our node we have finally selected here is a terminal one or not. And we can do this by writing value is terminal equals self.game.get value and terminated. And inside, so we are referencing this method right here. So here we just want to write state and action as the input. So we can take the state of our node here we have selected, and then also the last action that was taken. So just node.action taken. And we still have to remember one thing, and that is that the node always gets initialized this way. So the action taken was the action that was taken by the parent and not the node itself. So it was an action that was taken by the opponent from the node's perspective. So if we would actually have reached a terminal node, and if we would get the result that, a player has won here, then the player who has won is the opponent and not the player of the node itself. So if we want to read this value here from the node's perspective, we would have to change it around. So here inside of our game method, we should write a new method, def get opponent value. And here we can just say negative value. So if from the parent's perspective, we have got a 1 right here as a return. We would like to turn it into a -1 from the child's perspective, because it's the opponent that has won and not the child itself. So let's use it right here. So let's say value equals self.game.get opponent value of the old value. And we should also keep one thing in mind, and that is that we're using this node.actionTaken method right here, right? But actually, at the beginning, we just have our simple root node, and we can see that the root node is not fully expanded, right? Because it has all possible ways we could expand it on. So we will call this right here immediately with our root node. And the way we initiated our root node, we still have action taken is none, right? And if we call this method right here with action taken being none, so we call this with action taken being none, and we'll move to check when with action being none, and then we will do this expression right here, and this will just give an error. So we have to say if action equals none, just return false, right? Because for the root node, we always know that no player has won since no player has played yet. So we can just leave it like this. Perfect. So now we're finished with all of this. And next, we want to check if this node is terminal. And then we could backpropagate immediately. And if not, then we would do expansion and simulation. So I'm writing now here if not is terminal. Then we want to do this right here. And at the end, we can just backpropagate, right? Okay, so yeah, now we can do expansion. And inside of this if statement, I can just write node equals node.expand. So we just like to return the node that was created by expanding here. And then inside of our node class, we can write a new method that will do the expansion job. So let's say def expand. Okay, nice. So the way expanding works is that we sample one expandable move out of these expandable moves we have defined up here. And then once we have sampled this move or action, we want to create a new state for our child. We want to act inside of this state. And then we want to create a new node with this new state we have just created. And then we'll append this node to our list of children here. So we can later reference it inside of our select method. And yeah, at the end, we can just return the child that was created newly. So for now, let's get an action here. And yeah, we want to sample it from above. So let's use np.random.choice. So this will just pick a random value out of a list on NumPy array. And inside we can say np.where. And then the condition is that self.expand moves should be equal to 1, right? Because the way we programmed it, all values that are 1 are actually legal, and we could expand on them. And with np.where, you always have to use the first argument you get when using the method. So yeah, this should work now. So yeah, we just first of all check what moves are legal, then we use np.where to get the indices from all legal moves. And then we use np.random.choice to randomly sample one indice. And this legal indice will then be the action we got, right? So that's great. And now we also have to make this move not expandable anymore, right? Since we already sampled it. So we can say self.expandable moves of action. And that should just be 0 here. Nice. So now we can create the state for our child. And at the beginning, we can just copy our own state. And now we would like to act inside of the state of our child. So we can say child state equals self.game.get next state. So we reference this right here. And then we can use state, action, and player. So let's move up again. So for state, we have just child state. And for action, we have the action right here. And for the player, we will use 1. So you might have noticed that we haven't even defined the player yet, which is weird, right? Because for TicTacToe, you have 2 players, obviously. But the way we will program our Monte Carlo tree search is that we will never change the player or never give the node the information of the player, but rather we will always change the state of our child so that it is perceived by the opponent's player. While the opponent's player still thinks that he is player 1, right? Even though, so the parent and the child both think that they are player 1, but instead of changing the player, we flip this state around. So we turn all positive numbers into negative ones and vice versa. And this way, we can actually create a child state that has a different player, but still thinks it's player one. So this just makes the logic much more easy for our game. And it also makes the code here valid for one-player games even. So that's very nice. So now we can say child state equals self.game.change perspective of child state. And then the player should be -1, right? Because in TicTacToe, when you change the perspective, or when you create a child node, you always want to be the opponent here. So let's write a new method, def.change perspective of a state and of a player. And in TicTacToe, we can just return the state multiplied with the player. So like I said, when we would change the perspective to player -1, so to opponent, then we would turn all positive ones to negative ones instead of our TicTacToe game. So nice. So now we have come here, and we have got, and our child state is ready now. So next we can just create the child itself, which is a new node. So let's say child equals node, and up here we can see that first of all we need the game, so it should just be self.game, then self.args, and then the state, which is just child state. And for the parent, we can choose ourselves as a node, and then for the action taken, we can use this action right here. We sent it above, so let's just take that. And now we want to append this child to our children. So I'm going to say self.children.append child right here. And at the end of our method, we can return the child we have just created. So awesome. That's the code finished here. So we have gotten this expansion part done. And after we have expanded, we want to do simulation. So from the video, you might remember that we performed these rollouts. And the way rollouts work is that we just perform random actions until we have reached a node that is terminal. And then we will look at the value, so the final outcome of this game, so who won essentially. And then we'll use this information, who won, to backpropagate basically, right? So nodes where the player of the node itself won after randomly choosing actions are more promising than the ones where the opponent won, right? So yeah, we use this for our backpropagation. So here we can just say value equals node.simulate. And then we obviously need to write a simulate method up here. So let's do that for now. So def simulate of self. And first of all, again, we have to check if this node that has just been expanded is a terminal one. So up here, we just say value is terminal equals self.game.get value and terminated. And inside, we can again use self.state and self.actionTaken. And we have to, again, flip this value around to the opponent's perspective, because always when a node has won, it's not because of the node itself, but because of its parent that has taken this action here. So we have to say value equals self.game.get opponent value of the value we have gotten here. And yeah, then we could just say if is terminal, then we would like to return this value up here. And in all other cases, we now want to perform our rollout. So in order to do that, we can just say rollout state equals self.state.copy. And then we'll say rollout player equals 1 at the beginning. And here we're actually going to use the player, and that's just because we need to find out if the value we got at the end should be perceived by this getOpponentValue method or not when we use it to backpropagate our node its value right here. So inside of our rollout, we can say while true. And then again, we want to sample an action like we did up here. So first of all, we can say valid moves equals self.game.get valid moves of the rollout state. And then here we can write action equals np.random.choice of np.where of valid moves equals 1. Take the first one here, and yeah, that should be our action. And now we can use that action to get the next state. So we can write rollout state equals, and then we can say self.game.get next state. And then again, we use the rollout state and the action here. And then for the player, we'll use rollout player. And after we have gotten our new state, we have to check again whether this state is terminal. So let's write value is terminal equals self.game.get value and terminate it. And we just use this newly updated rollout state as input and also the action we took. And now, if is terminal is true, we'd like to return our value. So let's write that as an if statement. And for the value, we again have to check whether we were rollout player 1 when we won the game or hit a terminal node. So we say if rollout player equals -1, then we would flip the value up so that we don't get a positive return since the opponent won and now it's we as a node. So we can say value equals self.game.get opponent value of value. And generally we can just return this value here like we did up here above. So nice. Now, in all other cases, if we haven't reached the terminal node immediately, we want to flip our player around. So we can say rollout player equals self.game.get opponent of the old rollout player. Yeah, so that should be it. So yeah, now we can do simulation after we have expanded. And the final step would now be to do backpropagation. And we can just write a new method here. So let's say node.backpropagate, and then we'll pass the value here as input. We have gotten either here or here. And we can write that here inside of our node class. So def backpropagate, and then take value here as input. So when we backpropagate, first of all, we want to add the value to our value sum, and then we want to add our visit count with just a 1, so count that up. And then we want to keep backpropagating up all the way to our root node. So let's write self.value sum plus equals value. And then let's write self.visit count plus equals 1. Then when we backpropagate up, we again have to remember that our parent is a different player than us. So we should write value equals self.game.get opponent value of value here. And then we say if parent is not none, which is always true except for the root node where we have this as our placeholder. Then we're just going to say parent.backpropagate value right here. And that should be it. So yeah, we have this recursive backpropagate method. And that should be all we need for our MCTS. So finally, we have gotten all of the results. We have backpropagated all of our visit counts and values and so on. So now we would actually like to return the distribution of visit counts. So to do that, we should just write a new variable action props, so the probabilities of which actions look most promising. And at the beginning, that should just be np.zeros, and the shape here can just be the action size of our game. So save.game.get.action size. So for TicTacToe, just this one right here. And now we want to loop over all of our children again. So let's say for child in self.children. And then we'll write action props at child.action taken. And this probability should be equal to the visit count of our child. So let's say child.visit count. And now we want to turn these into probabilities. And the way we do that is we just divide it by its sum, so that the sum will be equal to 1. And let's just write np.sum of action props right here. And then we can return this. Nice, so that's looking promising. So let's test this out. And there is still invalid syntax here, so I just have should remove this here. And now this is working. So let's test this out. And we can create the MCTS object here inside of our test script we used for the game. So let's write MCTS equals MCTS. And for the game, we'll use TicTacToe. And now we still have to define our arguments. So for C, which we use in our UCB formula, we can just roughly say that we want the square root of 2, which is what you might use generally. And then for the number of searches, we can set that to 1,000. Nice. So let's also pass on the args here inside of our Monte Carlo tree search. And then during our game, first of all, I should remove that. We should say that we only do all of this, so acting ourselves if we are player 1. And in all other cases, so in TicTacToe, when player is -1, we want to do a Monte Carlo tree search. So we can say MCTS props equals MCTS.search of state. But you should remember that we always like to be player 1 here when we do our Monte Carlo tree search. So first of all, let's write neutral state equals, and then we can say save.game.change perspective, and also not save.game but TicTacToe now. Yeah. And then we'll use this general state here. And for the player, we can just set a player, which is here always -1. So we always change the perspective. And then instead of an MCTS search, we should just use this neutral state we have just created. And that's great. And now out of these probabilities, we want to sample an action. And to keep things easy, we can just sample the action that looks most promising, and the way we do that is by using np.argmax. And this will just return the child that has been visited most number of times. And inside here, we can use the props of our MCTS. Yeah, and this is just the action we have here. So let's test this out and see if this works. Okay, so we still have a problem here. Oh, also for parent, we need to use self.parent. And here I have a typo. So just want to say best child. And here we don't want to use self.children, obviously, but the children of our root node. So instead of our MCTS, we can say for child in root.children. So perfect. So now we can see that this Monte Carlo tree search moved here instead of the middle. And now we as a player, let's play a bit stupid here to check this out. We can just play here, MCTS played here. Then we can say we play 7. And now the MCTS played here. And from the roots of TicTacToe, you know that the MCTS has hit 3 negative ones here instead of this row here. So it has 1. So nice. So now we can see that this MCTS is working well. Okay, so now that we have our standalone Monte Carlo tree search implemented right here, we can now start with building the neural network, right? So that we can then later use the AlphaZero algorithm in order to train this model that can understand how to play these given games, right? And before we start with building, let me just briefly talk about the architecture that we have for our neural network. So yeah, this is just a brief visualization here. And first of all, we have this state right here that we give as input to our neural network. And yeah, in our case, this state will just be a board position. So for example, a board of TicTacToe right here. And actually we encode this state so that later we have these 3 different planes next to each other, like in this image right here. And actually we have one plane for all of the fields in which player -1 has played. So where these fields will then be turned to 1s and all other fields will just be 0s. And then we also have a plane for all empty fields, and these will then be turned to 1s, or other fields being 0s. And then we also have this last plane for all the fields in which player +1 played. And yeah, here again, these fields will be turned to 1s and all other fields will be turned to 0s. So by having these 3 planes right here, it is easier for our neural network to basically recognize patterns and understand how to play this game, right? So essentially we encode our board game position almost so that it looks like an image afterwards, right? Because we have, instead of these RGB planes, we have these planes for player +1, player 0 or empty fields, and player -1, right? And because our state looks like an image, we also want to use neural network architecture that works best for images, right? So because of that, we have these convolutional blocks then inside of our neural network, right? So first of all, we have this backbone right here. And this backbone will just be the main part of our neural network, where we do most of the computation. And here for the backbone, like I said, we use these convolutional blocks. And we also use this ResNet architecture, so the residual network. And this is just a research paper that turned out to work really well with understanding images. And here basically what this ResNet architecture does is that we have these skip connections like this. So when we do the feed forward through our backbone, we won't just always update the X by moving forward, right? But rather we will also store this residual. So basically we store the X value, or the value that is passed through before we give it to our conf block. And then at the end, the output will just be the sum of the X value before our conf block and the X value after our conf block or conf blocks. And because of that, our model is much more flexible, because it could technically also mask out conf blocks by not changing the X at all and just using this residual skip connection X, right? So here's also just an image from the paper. So yeah, generally the main idea is to also store this X right here at this position as a residual, and then have the skip connection later on, so that the output will be the output from the conf blocks summed with the initial X. So this skip connection right here. So this is just the ResNet architecture that we use inside of our backbone, right? So after we have gone through our backbone, we split our model architecture into these 2 parts. So first of all, we have this policy head here above. And at the beginning here, we just have a singular conf block. And this conf block will take the output from our backbone as input like this. And then after we have gone through that conf block, we will then flatten out the results here. And then we just have this linear layer or fully connected layer between the outputs for our conf block and then also these neurons right here. And at the end, we just want to have 9 neurons in the case of TicTacToe, because we want to have 1 neuron for each potential action, right? And in TicTacToe, there are 9 possible actions. So at the end, we will just have these 9 neurons right here. And normally we would just get these logits, so just these standard outputs. But when we want to get this readable distribution telling us where to play, we also have to apply this softmax function. And this will basically turn the outputs from our 9 neurons to this distribution of probabilities. And then each probability will basically indicate us how promising a certain action is, right? Okay, so this is why we have these 9 neurons here, and then why we also in practice later call the softmax method, right? So the second head is this value head right here. And here we also have this singular conf block that is different from this one right here. So we have this connection here as well. And this also takes the output from our backbone as input. And then again, we would like to flatten the output of this conf block here out. And we want to have this linear layer or fully connected layer. And finally, we just want to have 1 neuron right here, because remember that this value head should tell us how good this state right here is. And it should just give a float in the range of -1 to +1 as output. And because of that, we only need 1 neuron, right? And the best way to get this range of -1 to +1 is by also applying this 10H activation function onto this last singular neuron right here. So here's just a visualization of the 10H function. And basically this will just squish all of our potential values into this range of -1 to +1. And this is exactly what we want for our value head. So ultimately we have this model right here that takes this encoded state as input. And on one hand, it will output the policy. So just, this distribution telling us where to play. And on the other hand, it will give us this value. So just this estimation telling us how good this state is right here. Okay. So now we can actually build this inside of our Jupyter notebook. And here the first thing is that we want to import PyTorch, because we want to use the deep learning framework PyTorch. So first of all, I will also print the np.version, so we always get that right here. And then we will import torch like this. Let's also print torch.version right here. Okay, so let's just do that. Okay, so this is my current torch version. And I think for the loss we will use later on, we will have this multi-target cross-entropy loss. And this has been added as a feature just recently to PyTorch. So I would just recommend to get this version right here, or any newer version. So if you have any problems, you can just use this one. And I also have CUDA support right here because of my NVIDIA GPU. But you could also just get the CPU standalone PyTorch version, depending on your setup, right? Okay, so now additionally to torch, we also want to import torch.nn as nn right here. And then we want to import torch.nn.functional like this, as this big F, right? Capital F. Okay, so now we can import these things right here. And then I will just create this model, and I will just create this new cell above our MCTS implementation. So I will just call this class resnet. Then we have nn.module and inherit from that. So here we have our init. And first of all, we have a game, and then we have a num of res blocks. So this will just be the length of our backbone, right, inside of our architecture. And then we also have num hidden here. So this will be the hidden size for our conf blocks, right? Okay, so inside, first of all, we have to call super.init. And now we can define the start block. And this should be equal to nn.sequential. And first of all, we will just have this conf block at the beginning, so nn.conf2d. And the input hidden size is just 3, because remember that we have these 3 planes at the beginning. And then the output dim should be num hidden. And then for the kernel size, we can just set that to 3. And also we can set padding to 1, right? Because when we have kernel size as 3 and padding as 1, this conf block won't actually change the shape of our game state directly. So it always will be number of rows times number of columns for these images, essentially, right? For these pixel values, if you want to look at it like an image. So after our conf2d, we also want to have this batch norm. So nn.batch norm 2d. And then here we have just num hidden as our hidden size. Yeah, and this batch norm will just increase the speed for us to train, essentially. So now we can also have this nn.value. And yeah, this value will just turn all negative values to zeros, so clip them off basically, and this way it's also faster to train and safer. Okay, so this is just our start block right here. So first of all, just this conf2d, then this batch norm 2d, and then our value. And now we can also have this self.backbone like this. This should be equal to nn.module list. And then here we just want to have this array, and basically want to have this array of different res blocks, right, inside of our backbone. Remember from this image right here. And in order to do that, we also have to create this res block class. So let's write class res block like this of nn.module. And then first of all, we have our init again. And then we just have num hidden as input here. And again, we have to init our super class as well, like this. Okay, so now for each res block, we also want to have our first conf block, so self.conf1. This should just be equal to nn.conf2d of num hidden for the input hidden dim, then num hidden for the output hidden dim, and then kernel size should be 3, and then padding should be 1 here. So this is our first conf block. Then we also have our first batch norm block, so bn1. This should be equal to nn.batch norm 2d of num hidden as the hidden dim. Then we can have our second conf block. So self.conf2 should be set to nn.conf2d, like this. And then again, we have num hidden here and num hidden here as well. And then a kernel size of 3 and a padding of 1. And now we can also define the second batch norm, so self.bn2, set that equal to nn.batch norm 2d of num hidden here as well. So then let's also define this forward method. So let's write def forward. Then first of all, we have self, and then here the x, so the input. And then remember that we, instead of our res block, want to have this residual, so that we can later have this skip connection. So let's create this residual and set that equal to x. And then now we want to update this x right here separately. And we can do this by, first of all, calling self.conf1 of x, then calling self.bn1 on top of that. And then also we want to have a value here. So just capital F dot value like this. And so this is our x at this position. And then we also want to feed through our second conf block here. So let's update x by calling self.bn2 of self.conf2 of x right here. So this way we have went through these two conf blocks right here. And then now we can just sum up this output with the residual, right? So x plus equals residual right here. And then now we can just again call the value here. So x should be f.value of x. And now we can just return that x right here. So this way we have this nice residual connection here. And at the end, we just return the sum, right? Okay, so now we actually can create this backbone right here. So in order to do that, we want to create a res block of num hidden just for I in range of num res blocks, like this. So this way we also have our backbone, right? So this is great. And next, we can create this policy head. So self.policy head, like this. This should again be equal to nn.sequential. And inside of the sequential, first of all, we want to have just this conf block, so nn.conf2d. And here we have a num hidden as our input hidden size. Then we have just 32 as our output hidden size. And then we can also define a kernel size and set that to 3 and have a padding of 1. And then again, we want to call it batch norm here. And just this value here. Okay, so after we have went through this conf block, remember that we want to flatten our results. So let's just call nn.flatten here. And now we want to have this linear layer, right? So nn.linear. And for the input, we want to have these 32 planes multiplied with the number of rows and multiplies with the number of columns. So times game.row count times game.column count, right? Because remember that we have a kernel size of 3 and a padding of 1 for all of our conf blocks. And because of that, we won't change the actual shape of our state, right? So because of that, we can just, when we want to get the input size of our flattened output here, we can just multiply the number of hidden planes, so 32, with the row count, with the column count here as well. Then for the output of our linear layer, we just want to have game.action size, right? Okay, yeah, so this is great. And now we can also define a value head. So self.value head, like this. And this should be set to nn.sequential. And here, first of all, we also have nn.conf2d. And for the input hidden dim, we have just num hidden. And for the output dim, we have just 3. And for the kernel size, we can set that to 3 and padding to 1 again. And now we can also have a batch norm here. So batch norm 2d. And have 3 as the hidden size. And then again, call it just a value on top of it. And flatten our results here. Okay, so now we also want to have this linear layer at the end. And again, for the input, we have just 3 times game.row count times game.column count. And then for the output, we just want to have 1, right? Because we just want to have 1 neuron here. And then also we want to have this 10h activation function, right? So we can just add nn.10h right here. So now we have this part here finished. And next we can write this forward method for our ResNet class. So it's right there forward and take the input x here And first of all, we want to send this x through our start block. So x should be self.start block of x, right? And then we want to loop over all of our rest blocks right here instead of our backbone. So let's write for rest block in self.backbone like this. And then here we can just set x to the rest block of x, right? So this is great. And now we have these x values right here. And next we can just get this policy and this value here back. So first of all, we can write policy, and here we can just set that equal to self.policy head of x. Then this value should be self.value head of x. And now we can just return our policy and our value right here. Okay, so let's just run that for now. And now we also want to test that this is working. So I would just create this new cell right here. And here let's just start by creating a game of TicTacToe. So this should be equal to this TicTacToe class right here. And let's get this state by calling TicTacToe.get initial state like this. And then let's just update that state by first of all setting state to TicTacToe.get next state of state. Let's just say that, I don't know, we play at the position 2 for the player -1, or positive 1 in this case, and let's also play at position 7 for the player -1. Okay, so now we can just print the state for now. And yeah, we get this state right here. Okay, so next we should remember that we also have to encode our state when we give it to our model. So we also have to write this new method right here. So here we just write def get encoded state of self and then just of the state right here. And remember that we want to have these 3 planes, right? So we can get this by writing encoded state equals np.stack. And then here we want to stack, first of all, the state for all fields that are equal to -1 with the state of all empty fields, so that the fields that are equal to 0, with the state where for all of the fields that are equal to +1, like this. So yeah, this should be our encoded state. And here these will just be booleans, but rather we want to have floats. So let's just set the type here to np.float 32. And now we can just return this encoded state. Okay, so let's test this out by writing encoded state and setting that equal to TicTacToe.get encoded state of this state right here. And let's just print that here. Okay, so yeah, now we see that we have this just state right here, and this is our encoded state, right? So first of all, we have this plane for all of the fields in which player -1 is played, so just this field right here, which is encoded as a 1 here. And then we have these empty fields right here, and then we also have these fields where player +1 played, so just this field right here, right? Okay, so this is great. And now we want to get this policy and this value, right? So first of all, we have to turn this state to a tensor now. So because of that, we can write tensor state and set that equal to torch.tensor of encoded state like this. And then when we give a tensor to our model as input, we also always need this batch dimension, right? But here we just have one state and not a whole batch of states. So because of that, we have to unsqueeze the zeroth axis. So what this does is that it will essentially just create further brackets around this encoded state right here. And this way we can pass it through our model, right? Okay, so now we have this tensor state right here. Then we can get this policy and this value by calling our model. First of all, I need to define our model. So let's write model equals res net. And for the game we have TicTacToe. For the number of res blocks, we can just set that to 4. And for the num hidden, we can set that to 64. Okay, so now we can write policy and value equals model of this tensor state right here. And then we want to process the policy and the value. So let's first of all get this float from our value by calling value.item right here. Since this will just be a tensor and we rather like to have the float, and we get this by calling .item on this tensor here. And then we can also change the policy. So here we can just write policy equals torch.softmax of this policy right here. And for the axis we have to choose 1 because we don't want to apply the softmax on our batch axis, but rather on this axis where we have these 9 neurons, right? So this is axis 1. And now we first of all have to squeeze this again so that we remove the batch axis essentially. And then we can detach that so that we don't have a grad here when we turn this to NumPy now. So then let's also take this to CPU. And let's call this to NumPy here, like this. Okay, so now we have this policy, and let's just print out both of these things. So print out the value and print out the policy and see whether this works. Okay, so nice. Now first of all, we get this value of 0.3 for this state right here. And then this is our policy distribution telling us where to play. So just this number of probabilities. Now, you know what, let's also make this a bit more visual. So let's import matplotlib, like this, .pyplot, right here, as plt. And then here we can just write plt.bar, first of all, of the range from our TicTacToe.action size, and then these policy values right here. Let's just write plt.show. Okay, so yeah, nice. So this is basically how our policy looks like. So for each action, we have this bar right here, telling us how promising this action is. And then obviously our model was just initiated randomly currently, so we can't expect too much here. So nothing actually, but when we later have this trained model, we can expect this nice distribution of bars telling us where to play, right? Okay, so now we also have this model built, and next we can start with incorporating our neural network into this Monte Carlo tree search, right? So before we do so, I'd still like to apply a small change here. So let's just set a seed for torch so that we have reproducible results, so that you can make sure that you at least build something similar to what I've built right here. So let's write torch.manual seed, and let's just set the seed to 0 like this. So perfect. And then we can update this Monte Carlo tree search right here. So the first thing is that we now want to give a model here as input. So this will later on just be our ResNet. So let's also declare self.model as model. And then there are 2 key changes we want to do. So basically, after we have reached a leaf node, we want to predict a value and a policy based on the state of our leaf node. And then we want to use this policy when we expand, so that we can incorporate the probability inside of the policy into the UCB formula, if that makes sense. So that when we choose a node during our selection phase, we are more likely to choose nodes with higher policy values, because these were the ones that seemed more promising to our model, right? So we want to choose these more often and walk down the tree inside of these directions where our model guides us. So this is the one thing we use our model for. And the next thing is that we want to use the value we get from our model to backpropagate once we have reached the leaf node. So actually we can completely remove this simulation part. So we don't want to do any rollouts with random actions, but instead we just use the value we get from our model. So let's call this right here. So we can write policy and value equals self.model. And here we want to pass in the state of our node, right? But remember that we want to encode it beforehand so that we have this 3 planes based on the players we have in TicTacToe or just for the empty fields, right? So you might remember this from the last checkpoint. So first of all, we can write self.game.get encoded state. And here we just have node.state. And now we want to turn this encoded state into a tensor instead of just a NumPy array so that we can give it as input to our model directly. So we can write torch.tensor of self.game.getEncodedState of node.state. So now we have to unsqueeze at the zeroth axis. And so let's write unsqueeze of 0 right here. And this is because we always need an axis for our batch, right? And currently we aren't batching any states. So we just create this empty batch basically with just this one state right here. So this is why we unsqueeze here. And yeah, then we get a policy and a value as result. And now remember from the model checkpoint that we want to turn this policy, which is just which are just logits currently, so just 9 floats. We want to turn this into a distribution of likelihoods. So first of all, we can write policy equals torch.softmax of policy. And then we have to set axis to 1 because we want to apply the softmax not on the batch axis, but rather on the axis of our 9 neurons, right? In the case of TicTacToe. So after we have called the softmax, we would like to squeeze again at the 0th axis so that we remove this batch axis now. So actually we want to revert this statement right here after we have feed forwarded our state through our model. And next we can call CPU in case we might use GPU later, and then we can use NumPy right here. And also we should use the torch.noGrad decorator on top of our search method. So because we don't want to use this policy and value for training immediately, rather we just want to use it for prediction. So we don't want to store the gradients of these tensors right here. So we just use noGrad as a decorator. So this way, it's faster to run our Monte Carlo tree search. So great. So now we have our policy and we have turned it into a NumPy array and we have applied the softmax activation function. But next we also want to mask out all of the illegal states, all of the illegal moves, I'm sorry, because when we expand, we don't want to expand inside of directions where a player has already played, for example, right? So we have to mask out our policy on these illegal positions. So we get the valid moves, first of all, by calling self.game.getValidMoves. And then for the state, we can just use node.state, so the state of our leaf node right here. And then we want to multiply our policy with these valid moves. So now all illegal moves will have a policy equal to 0, which is great. But again, we have to rescale our policy so that we have percentages. And we do this by just dividing with its own sum so that the sum of our policy will turn to 1. And yeah, this will give us this nice distribution we want. So let's actually also change the value, and we want to just get the float from our 1 neuron of our value head. So we get this by calling value equals value.item. So in PyTorch, if you call .item on a tensor that has only 1 float, you will just get the float as result. So this is great. So now we have our value and we have our policy. So then we want to use this value for backpropagation, and we want to use this policy for expanding, right? So let's call node.expand with the policy as input, and let's remove this simulation part directly so that we will use this value right here for backpropagation later on, in case we have reached a leaf node here and we expand, right? So this is great. And now there's some smaller things we can just remove. So first of all, we can just completely delete the simulation method here. And then there are some more things. And first of all, when we call the expand method, we immediately expand in all possible directions because we just have this policy right here, and it doesn't make sense anymore to only expand in one direction once you had reached a leaf node, but rather we expand in all directions immediately. So this also means that we don't need these expandable moves right here anymore, because we will check the expandable moves by calling .valid moves later on. So also we can change this is fully expanded method here. And now we can just check whether the len of our children is larger than 0. Because remember, when we expand once, we expand in all directions. So if we have one child, we know that there aren't any more children we could have, right? So yeah, this should be enough here. So yeah, now this is working. But next we have to update this node.expand method right here. So let's do that here. So first of all, we take this policy here as input. And then we want to loop over our policy, right? So we can write for action and then prop. So just the probability at a certain action in enumerate policy. And then we can check for each action whether the probability at the given action is larger than 0. So let's write if prop is larger than 0. And we can remove these two statements here. And if this is the case, let us just create this new child right here, and let's append it to the children. But remember that we want to use this probability here inside of our UCB formula later on during selection. So we want to store this probability inside of our node object. And we do this by creating this new prior input here. So let's just set prior to 0 by default. And let's define self.prior here as prior. So the prior will just be the probability that was given here when we initiated the child, and it is equal to the policy as the given action from the parent's perspective when we expanded our parent. So now we have defined this prior right here, but we also want to use it here when we create a new node. So let's just give here prop as input for the prior at the end, like this. So great. So now we have all of this ready. So next we have to update the UCB formula, since AlphaZero uses a different UCB formula than just a standard Monte Carlo tree search. So I just brought an image up right here. So actually we remove the math.log and we just wrap the square root around the visit count of our parent. And then also we just add a 1 to the visit count of our child. And yeah, so that's basically it. So first of all, we have to say that if we call this UCB formula on a child that has a visit count of 0, then we can't calculate a Q value, right? So let's just set the Q value to 0 in that case as well. So let's say if child.visit count equals 0, then Q value should equal 0, and then else, Q value should be equal to this formula right here. So because now we don't backpropagate immediately on a node that has just been created during expanding. So it is actually possible now to call this UCB method on a child that hasn't been visited before. So yeah, this way we change this part right here. And then also we want to update this part here below. So let's write it like on this image here. So let's first of all remove this math.log from here. And then here we want to add a 1 on the visit count of our child. And then we also want to multiply everything up with the prior of our child, right? So that we also use the policy when we select downwards the tree. Yeah, so this should be working now. So let's see if we got everything ready. So yeah, I think that's it. So let's just run this right here. So first of all, we just update c to be equal to 2. And then we can create a model right here. So let's write model equals ResNet. And then for the game, we can just use TicTacToe. For the number of rest blocks, let's just say 4. And for the number of our hidden planes, we can just set that to 64. And then, you know what, also eval our model right here. So currently this model has just been initiated randomly, right? So we can't expect too much, but let's try this out. So, we're still missing the model here's argument inside of our MCTS. So yeah, like this. So nice. So now we see that with our updated MCTS, we played right here. And you know what? Let's say we would like to play on 1. So yeah, the MCTS played here. And let's play, I don't know, just on this 8 right here. And the MCTS played here, so -1, and has won the game. So now we have our updated Monte Carlo tree search ready. And next we can actually start to build this main AlphaZero algorithm. So in order to do that, let us just create a AlphaZero class. And I will define that just below our updated MCTS. Sorry, let's remove that here. And define it down below here. So let's write class AlphaZero. And for the init, we'd like to take the model, then also an optimizer. So this will just be a PyTorch optimizer like Adam we will use for training. And then also a game and some additional arguments here as input. And next we can define all of these things right here. So let's write self.model equals model, self.optimizer equals optimizer. And then write self.game equals game, and self.args should equal args as well. And at the end, we can now also define a Monte Carlo tree search object inside of our AlphaZero class. So let's write self.mcts should be equal to mcts. And when we initiate our Monte Carlo tree search, we want to pass in the game, the args, and the model. So let's just write game, args, model, just like this. So yeah, this is just the standard init of our AlphaZero class. And then next we want to define the method inside. And from the overview, you might remember that we have these two components, which is the self-play part and then the training part. And outside, we just have this AlphaZero wrapper right here. So let's create our self-play method like this. And let's just pass that right now. And let's also create our training method like this. And let's pass that here as well. So next we can have this learn method. And this will be the main method we will call when we actually want to start this cycle of continuous learning, where we run self-play, get data, use this data for training, and then optimize our model, and then call self-play again with a model that is much smarter, right? So for this cycle, we want to, first of all, loop over all of the iterations we have. So let's say for iteration in self.args of num iterations. And then for each iteration, we want to create this memory class, so just the training data essentially for one cycle. So let's write our memory list here. So let's define memory right here. And then we want to loop over all of our self-play games. So let's write for self-play iteration in self.args of self, in range, sorry. We need to define range here. So in range of self.args of num self-play iterations, like this. And then for each iteration, we would like to extend the data we just got out of our self-play method. And we want to extend this to this memory list right here. So let's write memory plus equals self.self-play, just like this, so that we extend the new memory. And actually we'd like to change the mode of our model so that the model is now in eval mode, so that we don't have these batch noms, for example, during self-play. And now we want to move on to the training part. So first of all, we can write self.model.train like this. And then we can say for epoch in range of self.args num epochs. And yeah, for each epochs, we like to call this train method right here. And we like to give the memory as input. So let's write self.train of memory like this. So let's also add memory here as an argument. So that's great. And at the end of an iteration, we like to store the weights of our model, right? So let's write torch.save of self.model.static like this. And for the path, we can just write model and then the iteration instead of an f string, and write .pt for the file ending. So let's also save the static of our optimizer. So let's write torch.save of self.optimizer.static. Then for the path, again, we can write optimizer and then iteration. And take .pt as file ending here. And we have to turn our string into an f string. Yeah, so this is great. And now that we have gotten our main loop ready, we would like to focus on this self-play method right here. So inside, we again have to define a new memory. So this will just be the memory inside of one own self-play game. And then we have to define a player at the beginning. So let's say player should equal 1 at the start. And then we also have to create an initial state, and we get the state by calling self.game.getInitialState like this. And then we want to have this true loop, and inside of this loop, we want to first of all call the Monte Carlo tree search based on the state we have. And then we want to get these action props as result. And next, we like to sample an action from this distribution of action probabilities. And so after we have sampled an action, we want to use this action to play, essentially. So we will get a new state by calling self.game.getNextState based on the old state. And then once we have this new state, we want to check if this state is a terminal one, so if the game has ended. And if indeed the game is ended already, then we want to first of all return all of this data to the memory here. And the data should be structured in this tuple form, where for each instance we have a given state, we have the action probabilities of our MCTS, and then we have the final outcome, right? So whether the player who played at the instance also was the player that won the game at the end, or the player that lost the game, or the player that hit and draw, right? So this should be incorporated in the final outcome. So we can write while true like this. And here, first of all, we have to remember that when we call MCTS.search, we always like to be player one. So we first of all need to get this neutral state. And we can get this by calling self.game.changePerspective. So let's write it right here. And for the state, we just like to take the state right here. And for the player, we just want to take the player above. And yeah, so that's great. So now that we have our neutral state, we can get our action props back from this MCTS search right here. And we call self.mcts.search, and we take this neutral state as input. So now that we have our neutral state and our action props, we can store this information inside of our memory so that we can later use this information to gather this training data. So first of all, we can write self.memory.append. Then we append this tuple right here of the neutral state and the action props, and then also the player. So yeah, now we want to sample an action out of the action props, right? And we can do this by calling np.random.choice. And for the number of different options, we can use the action size of our game. So in this case of TicTacToe, that is equal to 9. So let's say self.game.action size. And then for the probabilities we use for sampling, we just want to use these action props right here we got from our MCTS. So like this. So now that we have sampled an action, we like to play based on this action, right? So we can say state should equal self.game.get next state. And we give the old state, the action, and the player here as input. And now that we have gotten our updated state, we want to check if this state is terminal or not. So we write value is terminal equals self.game.get value and terminated. And we give the updated state and the action we use to get this updated state here as input. And then we can say if is terminal is true. So if is terminal, then we want to return this data, right? So first of all, we can write return memory should be equal to this new list right here. And then we want to loop over all of these instances inside of our memory. Oh, sorry, let's not write self.memory, but rather memory just like this, because we want to use this memory right here. So we can write for hist neutral state, hist action props, then hist player in memory. And for each instance, we now want to get the final outcome, right, at the given instance, because we need to store that inside of our training data. So we can say hist outcome, and this outcome should be equal to this value right here if hist player is also equal to the player we were when we achieved this value, right? So if we were player +1 when we played here and have indeed won the game, then we will receive a value as +1 as well. And we want to set the hist outcome for all instances in which player +1 played to +1. And we want to set the hist outcome to all instances in which player -1 played to -1, right? So hist outcome should be equal to value if hist player is equal to player. And then else we just want to receive the negative value, right? And now we can append this information to our return memory. So let's write return memory.append. And yeah, again, we need to append a tuple, so have brackets inside of these brackets right here. And we want to append the neutral state, but remember that we like to encode this state when we give it as input to the model, so we can already encode it right here. So let's write self.game.get encoded state of is neutral state for the state, and then just the action props from our MCTS distribution. And then just the hist outcome we got here. Yeah, so just like this. And sorry, we want to append this to our return memory, but not return immediately. But after we have looped through all of this, we now can actually return this return memory. Just like this. And in all other cases, if we haven't reached the terminal node yet, then we want to flip this player around so that we are player -1 now, if we were player +1 previously. So let's write player equals self.game.get opponent of player like this. So there's still some minor things I would like to update right here. So first of all, let's make this code more general by changing negative value right here to the value as perceived by the opponent, depending on the game we have inside of our AlphaZero implementation, so that we could also run this in games where we have only one player. Right, so let's write self.game.get opponent value of value like this. So this is just more general if we call this method right here. So get opponent value. And the next thing would be that we want to visualize these loops right here. And the way we can do this is by having these progress bars. And we can get them by using the tqdm package. So let's write import tqdm.notebook. And you know what? From tqdm.notebook, we want to import trange like this. So then we can just replace these range calls below with trange. So just a small difference right here. And now we want to check that this AlphaZero implementation is working as we have built it so far. So we want to create an instance of AlphaZero, and in order to do that, we need a model, an optimizer, a game, and some arguments. So we get the model, first of all, by building a ResNet, but initially, let's just create an instance of TicTacToe. So let's write TicTacToe equals TicTacToe like this. And then we can write model equals ResNet. And for the game, we want to use this TicTacToe instance we've just created. And for the number of res blocks, we can just say 4. And for the hidden dim, we can just say 64. And now we want to define an optimizer, right? So let's use the Adam optimizer as built in PyTorch. So let's write optimizer equals torch.optim.adam. And then for the parameters, we want to use the parameters of our models, just model.parameters, like this. And for the learning rate, we can just use 0.001, just a standard learning rate for now. And next, we also need to define these arguments right here. And we can do this by creating just another dictionary. And for the exploration constant, we can just choose 2 again. For the number of searches, we can choose 60. And then for the number of iterations on the highest level, we can just choose 3 for now. And then for the number of self-play iterations, so the number of self-play games we play for each iteration, self-play iterations. We can set that to 500 for now. And the number of epochs can just be equal to 4 currently. You know what, let's also lower this amount to 10 for now so that we can see that we can save our models. And let's just run that right here. Oh, sorry. And now we want to create this instance of AlphaZero. And this should be equal to this AlphaZero class. And the input should now be this model we have created, the optimizer we have created, and the game and arcs we have created. So let's write model optimizer. And for the game, we can write TicTacToe. And for the arguments, we can use the arcs here. And then we can run AlphaZero.learn like this. Let's see if this works. So nice. So now we get this good looking bar. We can see that we are running these self-play games. Great. So now we can actually implement the training method inside of our AlphaZero implementation. So let's just change this method right here. And the first thing we always want to do when we call this method is that we want to shuffle our training data so that we don't get the same batches all the time. So we can do this by calling random.shuffle here of the memory. And if we want to use this, we have to import random here above. Just like this. And nice. So now we can actually continue with this implementation right here. So next we want to loop over all of our memory, and we want to loop over it in batches, right? So that we basically have a batch index. And for each batch index, we can then sample a whole batch of different samples and then use these for training. So the way we do this is by writing for batch index in range. And here we want to start at 0. We want to end at the len of our memory. And then we want to step in the size of self.arcs.batch size. And now we want to take a sample from our memory, right? And we can get this sample by calling the memory at the batch index at the beginning. And we want to call it until batch index plus self.arcs.batch size. But just remember that we don't want to call it on any batch index that might be higher than our len of the memory. So we have to be careful here, and we can check that we don't exceed the len of our memory by calling min of len of memory -1. And then the batch index plus self.arcs of batch size right here. So this way we won't ever exceed this limit currently here. So now we want to get the states, the MCTS props, and the final rewards from our sample. And we can do this by writing state and policy targets for the MCTS distributions and value targets for the final reward we get from self-play. And we get this from our sample by calling the zip method. So the way this works is that we basically transpose our sample. So currently we have just this list of tuples, and each tuple contains a state, a policy targets, and a value. But by applying this asterisk here and then zipping it, we actually get lists of state, lists of policy targets, and lists of value targets. So we transpose this sample around, basically. So now the state is a list full of NP arrays. The policy targets is a list full of NP arrays, and value targets is a list full of NP arrays. But it's much more helpful if we actually have all of these things as NP arrays immediately. So let's change them by saying value and policy targets and value targets. And these should be equal to np.array of state and np.array of policy targets and np.array of value targets like this. But remember for the value targets that currently we only have this numpy array, and inside we immediately have all of our float values. But it's much more helpful if each of these value actually is in its own subarray later on if we compare to the output of our model. So we can change this by calling reshape here. Then we say -1 for the batch axis, and then we just say 1 so that each value will be in its own subarray essentially. So this is great. And now we can turn all of these three things into tensors. So first of all, we can write state equals torch.tensor of state. And for the d type, we can just say torch.float32. Even though, this encoded state might be in just integers right now, not in floats. So that's nice to change the d type here. And for the policy targets, we want to also turn this into a tensor and change the d type to float32. Let's torch.tensor like this of policy targets here. Yeah, and then the d type should be equal to torch.float32 like this. And then we have our value targets. And here we also want to turn these into a tensor and have value targets as the old input. And the d type again should be equal to torch.float32. So great. So now we have all of our tensors ready. And the next step is to get the out policy and the out value from our model by letting it predict the state we have here. So let's write out policy, out value equals self.model of the state right here. And then now we want to have a loss for the policy and a loss for the value. And we can first of all define the policy loss. And you might remember that this is a multi-target cross entropy loss. So here we can write f.cross entropy like this. And then first of all, we have our out policy. And then we have our policy targets. And so next we have our value loss. And here we use the mean squared error. So we can write value loss equals f.mse loss like this. And then first of all, we have our out value, and then we have our value targets. And now we want to take the sum of both of these losses to finally get just one loss. So we can write loss equals policy loss plus value loss right here. So now we want to minimize this loss by backpropagating. So first of all, we can write optimizer.zeroGrad. Then we want to call loss.backward. And then we want to call optimizer.step. So this way PyTorch does all the backpropagation for us and actually optimizes this model right here. So this way we now have a better model, and then we can use this during self-play. So let's test this out. So here I will just call this again. You know what, let's actually set num self-play iterations to 500 now. And I will now test this for the number of iterations we have here. And then afterwards, we can finally see how this model has learned. And feel free to train as well, but you don't have to. And we will make it more efficient later on. So we can also just test it here on my machine. Okay, sorry. So I forgot to define a batch size right here. So let us just pick 64 as our default batch size. And then we can run this cell right here, and we get these nice progress bars during training. And I have just trained this cell right here, and it took roughly 15 minutes just using the CPU of my machine. So now we actually have trained for a total number of 3 iterations. And remember that we save our model at each iteration because of this expression right here. So now let us actually check what the neural network we have trained understands of the game. And we can do this by moving up to this cell right here. So this is just where we tested our randomly initiated model. So here when we define our model, let us actually load the state dict. So let's write model.load state dict. Inside we can write torch.load. And for the path, we can write model and then 2, since we want to check the last iteration. And then pt for the file ending. And you know what? Let's also put our model in eval mode. So let's just run this right here. And then for this state right here, we get this distribution of where to play. So our model tells us that either we should play in the middle right here as player positive 1, or we should play on this field right here and the corner is player positive 1. And you know what? Let's also test it for this state right here. So 2 and 4 is player negative 1. And then as player positive 1, we have played on the fields of 8 and of 6. So first of all, now you can see that we have copied this board state from the image right here. And yeah, then we also encode it. And then we get this distribution of where to play. So now the neural network correctly tells us that we should play on position 7 because we would win here. And yeah, for the value, we get a result that is close to positive 1 because we would just win if we play here. So we have a high estimation of this position right here as a player positive 1. So yeah, and this is even better than the distribution we have right here. So remember, this is just what this neural network as a mathematical function put out, and we never did a Monte Carlo tree search or anything when we got this result here. So we can perfectly see that this mathematical function, so this neural network, actually internalized the Monte Carlo tree search by playing with itself. And now we can just call this neural network with a given state, and we get this neat distribution of where to play, and also this nice float here telling us whether the given state is a good one or not for us as a player. Great, so now we can apply some tweaks to our AlphaZero algorithm. And the first tweak we want to add right here is that we want to also be able to use GPU as a device, since that might be way faster for training depending on your setup. So we can add GPU support by declaring a device right here. And for the device, we can say that it should equal to torch.device. And the device should be CUDA, so NVIDIA GPU, if torch.CUDA.is available. And then else we can just set it to CPU like it was initially. And yeah, we want to then use this device and give it to our model as an argument. So this also means that we have to add it right here to our ResNet class. So let's set device right here. And then we will first of all add it as a variable here. So self.device should equal device. And then we also want to set our model to the device it was given. So let's write self.toDevice right here, so that we turn our model to GPU, for example, if we have CUDA support on our machine. Yeah, so that's the first part. And now we also want to use this device, first of all, during self-play, and then second of all, during training, right? So let's move to the self-play part right here. And We use our model during self-play when we get these action props right here during our MCTS search, because we call our model right here. So when we get this policy and this value right here. And we also want to turn this tensor into a tensor that is on our device. We have declared, so we can do this by writing device should equal self.model.device like this. And now we also want to use GPU for or we want to add GPU support during training. So let's move to the training part right here. And we can first of all move the state to our device, since we use it here as input to our model. So let's write device equals self.model.device. And then we also use these policy targets and value targets, and we compare them to the outputs of our model. So we also have to move them to the device of our model. So let's write self.device. Let's write device equals self.model.device again right here. And also right here down below. Okay, so now we should have GPU support as well, so that was fast. And now there are several more tweaks. So the next tweak we can apply right here is that we also want to add weight decay, since we have this L2 regularization in our loss for AlphaZero, like you can see on this image right here. So we want to write weight decay, and we can just set that to 0.001 like this. So this should be fine. And so now we have weight decay and GPU support added to AlphaZero. And next, we also want to add a so-called temperature. So remember when we sample an action from these action props right here. Currently, we just use the visit count distribution of the children of our root node as the probabilities. And then we take these probabilities for sampling, right? But actually, we want to be more flexible, because sometimes we would rather like to explore more. So also, sometimes take visit count, take children or actions more often that haven't been visited that often. And sometimes we also want to exploit more. So we want to tend to always just pick the actions that look the most promising to us. So the way we add this flexibility is that we get some temperatured action props. So we basically tweak these distribution right here, and then we will use the tweak distribution as the probabilities when we sample an action. So let's write temperature action props like this. And we get these by, first of all, using the old action props. Then we want to power them by 9 divided by self.args.temperature. So like this. And now we also have to define temperature in our args right here. So let's write temperature and set that to 1.25 in this case. So now we have declared this temperature right here. And actually what this does, in the case for a temperature that is larger than 1, you can see that the number we use for the power actually gets much smaller. And what this then does as a result is that we squish all of our probabilities much closer together, so that we actually do more of exploration, because the higher our temperature actually gets to infinity, the more it would be as if we would just take completely random actions sampled from just this random distribution. And on the other hand, if our temperature would move down, we can see that this number would actually move up. So if our temperature would turn to 0, for example, or close to 0 and not 0 directly, then it would be as if we would take just the argmax of our distribution right here. So we want to do exploitation and not exploration, right? So this temperature right here basically gives us the flexibility to decide whether we want to rather take more random actions that do exploration, or whether we just want to exploit and take the actions that look most promising at the current time. So yeah, this is great. And now we also have our final tweak we want to add to AlphaZero. And that is that we also want to apply some noise to the policy that was given for our root node at the beginning of a Monte Carlo tree search. So when we give our root node a policy, we basically want to add some noise so that we also explore more and move in some directions that maybe we haven't checked before, so that we also make sure that we don't miss on any possible promising actions. So the way we add this noise to our root node is that we first of all have to add these statements to the top right here as well, so that we also add the policy at the beginning and basically separate that from the steps right here. So first of all, we should get a policy and a value by calling self.model. And then here inside we have torch.tensor. Then we have self.game.get encoded state. Sorry. And then for the state, we can just take the state of our root, but this is equal to this state right here. So let's just take this one. And for the device, again, we want to use the device of our model so that we could use GPU. So self.model.device right here. And then again, we have to unsqueeze at the end so that we have a access for our batch. So this is great. So now we get this policy and this value. And actually, let's just turn this value into a blank variable because we don't need it at the top. So this should be more readable now. And now we want to again tweak our policy. So we have a typo right here. So let's first of all use softmax right here. So policy should equal to torch.softmax of policy. For the axis, we want to use the first axis, so that we don't use the softmax on the batch axis. Then again, we have to squeeze at the end, turn our tensor to a CPU, and then just get the NumPy array out of it. So now again, we want to get some valid moves, and then multiply our policy with them, so that we mask out the illegal moves. So valid moves should equal to self.game.get valid moves of state right here. And then policy should be multiplied with these. And then again, we can now add some noise right here. So after that, we would just again turn our policy to this distribution of probabilities. So we want to divide it with its own sum. So now here we actually want to add this noise to our policy so that we do some more exploration during a Monte Carlo tree search. So the way we can add this noise is shown here on this image. So first of all, this should be the updated policy for our root node. And then we get this updated policy by, first of all, multiplying our old policy with this coefficient right here. And this coefficient is just a number smaller than 1. So basically, we lower all of our policy values inside of the distribution. And then we add the basically opposite coefficient. So also a number smaller than 1. Multiplied with this noise right here. And this should just be our updated policy. So this epsilon value here is just a float smaller than 1. This n value right here is a noise called Dirichlet random noise. And we get this by just using np.random.dirichlet right here. And yeah, basically for us, this will just give this distribution of random values. And we basically will add them to our policy multiplied with this coefficient that is smaller than 1. So this way we basically change our policy a bit to also incorporate some randomness so that we then can explore more rather than just always walking down the tree in the way that our model tells us, because at the beginning our model doesn't know that much about the game. So we also want to make sure that we do some exploration as well. So let's add this right here. So policy should first of all be 1 minus self.args of Dirichlet epsilon, like this, and then multiplied with our old policy. And then we want to add this second part right here. So this should be self.args of Dirichlet epsilon again. And then we want to multiply it with np.random.dirichlet. And yeah, inside here we just want to use this alpha value. So give that as input to our np.random.dirichlet, and this alpha basically changes the way our random distribution looks like, and is based on the number of different actions we have for games. So in the case of TicTacToe, our alpha is quite high, so roughly equal to 0.3 if you just want to use it, because that turns out to be working well. But yeah, it might also change depending on your environment. Here then we want to use self.args.dirichlet alpha. Now let's actually move that to the next line so it's more readable. And then we want to multiply this array with the action size of our game. So and actually we also have to move this part here below so that we mask out our moves after applying this random noise and not before. So let's just copy them over below. Okay, great. So now we also added this noise to our policy. And now we can also use this policy we got right here to expand our root node. So let's write root.expand, and then just use this policy right here. And now there's just a minor change we can still add. And that is that currently, when we expand our root node at the beginning, we won't backpropagate immediately. So that means that our root node will have children, but the visit count of our root node will still be equal to 0. So that means that when we select right here, we will call this UCB formula with the visit count of our parent being 0. And if this visit count of our parent is 0, then basically this means that all of this will basically move away because we'll just turn to 0 as well. So this also means that we don't use our prior when we select a child for the first time. So actually, in order to make this better, we should just set the visit count of our root node to 1 at the beginning. So you know what, let's write visit count. Let's set that to 1 right here. And this also means that we have to add visit count right here and the default it should just be 0, but yeah, for the root node it should be 1 at the beginning, so that we immediately use the information of our prior when we select a child at the beginning of our Monte Carlo tree search. Okay, great. So now we can run all of these sets again and then see if this is working. So we also have to add Dirichlet epsilon here. And yeah, this should just be equal to 0.25. And then Dirichlet alpha. And I just set that to 0.3 like I told you. Okay, so now let's test this out. Okay, so we still have a CPU device somewhere. And let's see where that could be. Oh, I haven't run this right here. This is the error, sorry. So here we have to also add a device, and for this cell right here, you know what, let's just say torch.device of CPU, and then we can run this again. Okay, so perfect, now this is running. And yeah, for this current setup with TicTacToe, it shouldn't be that much faster, but later on when we use more complex games, GPU support will be much nicer. And also these other tweaks should help to make our model more flexible and actually make it easier to always get to a perfect model at the end. So nice. So I will just train this again. Feel free to also train it, but you don't have to. I've also uploaded all of the weights, and you can find them on the link below in the video description. So let's just train that, and then we can briefly check it again. And then we will also expand our agent so that we can also play the games of ConnectFour as well to TicTacToe. So see you soon. Okay, great. So now I've trained everything right here, and now we also want to check that our model has learned how to play the game of TicTacToe. So in order to do that right here, we have to move up to this cell again. And then you know what, let's also define a device right here. So let's write device equals torch.device of CUDA if torch.CUDA.is available right here. And then else we can just use CPU for our device. And then first of all, we want to use this device right here when we define our model. And then we also want to use this device for the tensor state. That is the state we'll use for the model to predict the policy and the value. So let's write device equals device right here as well. And then we also have to use the device when we load the state dict from this file right here. And that is when we have a map location. So that's right, map location equals device here as well. So now let's just run this again. And we see that we get this nice distribution and this nice value again. So we can also see that our model has learned. And by the way, here we aren't even masking out our policy. So the model has learned itself that, no, these moves aren't that great right here, because so you can't even play here because someone else has played without us even masking these illegal moves out. So that's nice. And now we can move on to also train our model or AlphaZero on the game of ConnectFour. Great. So let's also define a class for the game of ConnectFour. But before we do that, let's also add this representation method to our TicTacToe game. So let's write def wrapper like this, self. And then here we can just return the string of TicTacToe. And this string is also the result we would get when we call this object here instead of a string representation. So this means that we can use this information down below when we save our model for each iteration during learning. So we can just add self.game right here. So basically, we'll also add the name of our game to this model and this optimizer weight or statics when we save them, so that we won't overwrite our models when we train for the game of ConnectFour. Yeah. So this is great. And yeah, now that we have done this part, let us actually just copy this game over right here. So this is great. And now let's use it to define the game of ConnectFour. And for the game of ConnectFour, first of all, we have a row count that is equal to 6. We have a column count that is equal to 7. And then the action size is just equal to the column count. And then also let's add a variable for the number of stones you need in a row to win the game. So let's write self.in a row. And let's set that equal to 4. And for the representation, we can change the string to ConnectFour here. And yeah, the initial state can stay the same because we just want to get this blank array with row count being the number of rows and column count being the number of columns. So that's great. And now we have to change this getNextState method right here, because this action will just be a column, so telling us where to play. And the first step now is that we have to get a row back. And we get this row by looking at the given column. Then we want to look at all of the fields inside of this column that are equal to 0, so that are empty currently. Then we want to basically take the deepest empty field inside of this column, because this is where we would play in ConnectFour. And this would just then be the row we use for playing. So we get this by calling np.max, since in a numpy array, you start at 0 at the top and then your values get higher if you move down, basically in the rows. So we take np.max of np.where of the state at the given column. And the state here should equal to 0, right? So np.where will just again give us the indices of all of the empty fields, and then np.max will give us the highest indice, because this is where we would play in ConnectFour, because the stone would just fall down until there is this already non-empty field. So now we have a row, and technically we also have a column because of this action right here. So we can now write state of row of column and set that equal to this player right here we have given here as input. And so now this is great. And next we want to move over to this method right here. So we have this these getValidMoves right here. And for the getValidMoves, we just want to check the row just at the top. And then we want to see whether the fields at this row are equal to 0 or not. And these are our ValidMoves. So we can just write state of 0. So at the basically upmost row. And then this should be equal to 1 if it is valid. And otherwise we just have an illegal move on this given action. Okay, and now we want to check for the win, and frankly I'm just going to copy this method over right here. So basically we do the same checking as in TicTacToe, where first of all we check for the vertical possibility of a win, and then for a horizontal one, and for these two diagonals based on this action right here that was given as input. It's just that compared to TicTacToe, it's a bit more complex, where we actually have to walk in both directions and then keep checking whether we have stones in these directions that are equal to our own player sign. Also have this getValueAndTerminated method, and this can just stay the same for both games. get opponent can stay the same, get opponent value can stay the same, change perspective also stays the same, and get encoded state, yes, also the same right here. And I just noticed a small mistake, and that is when we use get next state right here, we can't reference column because we have defined our column's action here from the top. So let's just replace column with action like this. And now we can check that this is actually working in practice as well. So we can do this by making our code more general. And here we just replace TicTacToe with game. Then we'll use game inside here. And we'll use game inside here as well. Use game like this. Use game here. And also game right here. So let's also remove this instance of TicTacToe. And yeah, this one as well. And yeah, so this should be fine. And yeah, now there should be no more instances of TicTacToe. And next, let's replace this game of TicTacToe with the game of ConnectFour. Let's set the number of searches to just 20 so we can validate. Let's say 100 here. And then let's change the size of our model to be equal to 9 for the number of rest blocks and 128 for the hidden dim, so that we have a larger model when we later train ConnectFour. And now we can check whether this is working or not. So first of all, we also miss the argument of device. So let's add that right here as well. So let's write torch.device of CUDA if torch.CUDA.is available like this, and then else we can just use CPU. And yeah, now we want to use this device instead of our model class. So let's use it right here. And yeah, so that should be fine. So let's run this again. Okay, perfect. So now we have this game of ConnectFour. Let's say that we want to play at the position of 5, sorry. And here we still have a problem. So Dirichlet epsilon is also not set right here. So let's copy these values over like this. But let's set Dirichlet epsilon to 0 so that we don't use noise here. Okay, so I've played here. The model has played here. You know what? Let's play at 1. The model has played at 0 again. Let's play at 2. Let's see where the model played. Played at 0 again. And then we can just play at 3 like this, and we have 1. So at least we checked that the game of ConnectFour is working now. But yeah, obviously our model is terrible because we don't do that many searches right here, and also we haven't trained anything yet. So obviously our model is garbage. But let's change that now. So let's also train a model for the game of ConnectFour and then again test our results here. And we can do this by just applying some minor changes right here. So first of all, we should also make this cell right here more general. So we write game, and then for the game we just will use ConnectFour here. And then we also have to set the game to just game here instead of the ResNet. And you know what? Because ConnectFour is harder to train, let's change the number of rest blocks to 9, and let's change the num of our hidden dimensions to 128. And then we also have to use game right here during our AlphaZero initiation. And then we can also slightly tweak these hyperparameters here. So first of all, for the number of searches, we want to use 600. Then for the number of iterations, we can use something like 8, maybe for now. And then for the batch size, we can also increase that to 128. So yeah, and next we can just run that. And this should take a lot longer. but we will also increase the efficiency of it later on. So feel free to just use the weights that I've uploaded in the description down below. So you don't actually have to train this all yourself, since it might, at least on my machine currently, take a couple hours. So see you soon. Okay, now I've trained AlphaZero on the game of ConnectFour using these arguments right here. And frankly, I've just trained it for one iteration, since even that one iteration took several hours to train, right? So now we want to increase the efficiency. So yeah, that will be way faster for us to train also for these rather complex environments. But yeah, so still it was nice to train for this one iteration, because now we can evaluate our model and find out whether we at least learned something. So let's move to this evaluation cell right here. And now when we create this model, we also want to load the state dict from the weights that we saved after we have trained for this one iteration here, right? So here, when we create our model in this line right here, we can write model.load state dict like this. Then inside we can write torch.load. And then we want to reference this path right here. And so we can write model. And for the iteration, we will just use 0, since we started 0 and we have only trained for one iteration. And for the game, we will use ConnectFour. And for the file ending pt again. And let's also define a map location and set that equal to device. So this way, if your device would change during training compared to evaluation, you could still load the state dict like this right here. So yeah, this might be nice. So let's run the cell again. And you know what, let's just play it 6 here. So yeah, now our model played in the middle like this. So let's just play it 6 again. And yeah, our model defend this position. So let's just, I don't know, play it 0 right here. And the model build up this tower right here. Let's play at 0 again. Model building up the tower. Let's just play at 0 again. And our model finished this tower right here, and thus it has won the game. So we can still see that our model isn't playing perfectly, and obviously I just played in the corners to check for some simple intuition about the game on the model side. Yeah, but we can still see that it is much better compared to the initial model we had, where it only wanted to play inside of this column right here, right? So that's great. And now we also want to increase the efficiency of our AlphaZero implementation, right? So actually now the main part is completely done, and you should have this intuitive understanding of how the algorithm works. But like I said, it would be nicer to increase the speed we got when training, and especially the speed during self-play, right? So how can we do that? And here we want to basically parallelize as much of our AlphaZero implementation as possible, because these neural networks are built in a way where we could batch up our states to then get parallel predictions for the policy and the value, especially when we run our self-play loop. So one maybe way in which you could parallelize this AlphaZero implementation here is by using a package like Ray that would basically create these threads that are independent from each other, and then basically use that to harness all of your GPU power. But I'd rather like to build this parallelized version in a more Pythonic way like this. So just inside of our Jupyter notebook again. So let's actually do that. So we will actually basically batch up all of these different states, then get policy and value predictions, and then distribute them again to our self-play games, so that we play several self-play games in parallel. And this way we can essentially drastically increase the speed of our AlphaZero implementation. So the first thing we want to do here is that we also want to add this argument of non-parallel games here to our dictionary. And for now, I'll just set that to 100. So the idea is that we want to play all of these self-play games in parallel. And then when we reference our model, we will batch up all of our states inside of our MCTS search. And this way we can drastically reduce the amount of times that we call our model in the first place. And yeah, thus on one hand, we fully utilize our GPU capacities, and on the other hand, we can just decrease the amount of times we call our model, and thus also have a higher speed, right? So the way we can change this or update our AlphaZero implementation is that first of all, we want to just copy this class here over. So I will just create this new class here, and I will call this AlphaParallel. And then we also want to update the Monte Carlo tree search. So I will also copy this class here over as well. And I will call this MCTS-Parallel like this. So let's write it like this. So yeah, now we have our parallel AlphaZero and MCTS classes. And yeah, here we want to change the implementation of the self-play method, and because of that also the implementation of this search method right here. So now that we have got this class, we also want to create a new class. And here we basically want to store some information of a given self-play game, so that we can outsource some information from our loop when we loop over all of these given games. So let's create class, and I will just call this SPG for self-play game. And then we can also have an init here. And for the init, we want to pass in a game, so TicTacToe, for example, or ConnectFour. And then first of all, we want to have a state here. So initially, this should just be the initial state of our game, right? So we can set self.state to game.get initial state like this. And then we also want to have a memory inside here. And this should just be an empty list at the beginning. And yeah, then we also want to store a root, and this should be none at the beginning. And we also want to store a node here. And this should also be set to none at the beginning. And yeah, so this is everything we need here for this class right here. And yeah, so this way we can later store some information here. Okay, so now we want to update this self-play method right here. So first of all, we want to call it less often, since every time we call this method, we will call it for 100 potential games that are played in parallel, right? So here, when we loop over our num self-play iterations, we want to divide that with the games we play in parallel. So self.args of num parallel games like this. And also when we create this self-play game class right here, I've just forgot to add this brackets right here, so we should just add them. Yeah. Okay. So yeah, inside here, first of all, we can remove this state right here, since we store our state in the self-play games, right? And then also we can rename this memory to the return memory, since this right here won't be the actual memory in which we store our state and action props and player tuples initially, but rather this will be the state that we will return at the end. So the list we currently have here, right, which we won't need later on. Okay, so then the player can stay just the same, because even though we play games in parallel, we will always just flip the player after we have looped over all of our games, right? So this way, all of our games in parallel will also always be at the same player, right? Because we always start at player 1, and then we can just flip for all games in parallel as well. Okay, so now we also want to store our self-play games here. So I would just call this SPGs like this. And maybe let's just, maybe like self-play games like this. And here we want to have a list of all of our self-play games. So one self-play game should be created using this SPG class we have defined below up here. And inside we want to pass the self.game we have here as our AlphaZero class. And we want to create a self-play game for SPG in range of self.args and then num parallel games, right? so this way we create this list for all of our self-play games. And yeah, we basically give them the game in each case. Okay, so now we have these self-play games right here. And next we want to change this while true expression here, because this way we would stop after one game has finished, but rather we want to keep running our self-play method until all of our self-play games are finished. So we can check this by saying while len of SP games is larger than 0. So we implemented this way that once a self-play game is finished, we will just remove it from our SP games list. Because of that, we can just check here whether we have any self-play games inside of our list, right? So great. So the next step right here would be to get all of these states of our self-play games, first of all, inside of our while loop. So let's get all of the states here. And we can get all of the states, first of all, as a list by saying spg.state for spg in sp games, like this. So yeah, this way we just have a list of all of our states that are stored inside of our class. And now we can turn these states into just a numpy array. So the best way to do this is just by calling np.stack here of this list of numpy arrays. And this way we will basically get one large numpy array, right? Okay, so here we have all of our states. And next we also want to get the neutral states. So first of all, we can just change the naming right here. And then here when we change the perspective, we just have to write states here instead of state. And now we will change the perspective for all of our states, basically in just one function call, right? So this way we can also increase the efficiency, since changing the perspective works the same way if we have several states, because we would just multiply our values with -1 in case that we have player set to -1. And here we can just do the same, right? So this is great. And now we can also pass these neutral states to our Monte Carlo tree search. And we have basically finished this part right here. So let's now change the Monte Carlo tree search method. So first of all, we want to now give states here as input. So these are the neutral states we have just created. And now we can also, first of all, change the order. So let's just paste this one here below. And then we can work on the policy and the value first. So let's move it like this. Okay, so first of all, we get this policy and this value. And like I said, we can also do this with all of our batched states. So this way we just get several policies and values back here as a return. And this is great. But we still have to keep two things in common. So first of all, we don't need to call unsqueeze here, because now we have a batch. So we don't need to create this fake batch access, right? And then we also have to update this getEncodedState method right here. So because the way it is currently implemented is only working if we pass it one state at a time. Because this getEncodedState method will create these 3 planes for the fields in which player -1 played, or these the fields that are empty, or the fields in which player +1 is played, right? So it will always first of all give us these 3 planes. And then inside of these planes it will give us the fields, right? But we want to change the order here, because on the first axis we basically want to have all of our different states, and then for each state we would like to have these 3 planes, right? So we don't want to have these 3 planes at the beginning, but after our batch axis, basically, right? If that makes sense. So we have to basically swap the axis of this encoded state right here, so that it would also work if we have several states and not just one that we use when we call this method here. So first of all, we can check whether we have several states or not, and we can check this by checking whether the len of state.shape is equal to 3, right? because normally the len of just one state would be 2, right, where we have the rows and then the columns. And if we also have a batch axis, then the len would be 3, because first of all we have the batch, then we have the rows, and then we have the columns. And yeah, so if this is the case, then we want to create this new encoded state like this. And it should basically be equal to np.swap axis like this. And then here we want to pass in the old encoded state. And then we want to swap the axis 0 and 1, right? So that we don't, so that basically the new shape should be the size of our batch, then 3, and then the number of rows, and then the number of columns, right? Instead of having 3, then the size of our batch, and then the number of rows and number of columns, right? If that makes sense. So basically we swap these axes right here. So this is great. And now we can also copy this over to the game of TicTacToe as well. And yeah. Oh, sorry, I just noticed that we had np.swap axis using an E here instead of an I. So that's just a small mistake. And let's update this for both of our games. And yeah, so this should be working now. Okay, so now we can keep updating this MCTS search method. So first of all, we now get these policies and these values back as return, right? At the beginning, we don't need our values, so we just get these policies, and we can rename the state here to states. And then when we keep processing the policies, it's nice that we call the softmax this way, but again, we don't want to squeeze, since we want to keep our batch axis the way it is currently. And then when we add the noise to this policy, we also have to make sure that the shape of our noise is equal to the shape of our policy. So we can add a size right here. And the size should just be equal to policy.shape of 0, right? So this way we basically create noise for each different states, so for each different self-play game essentially. Okay, so this is great. And now we have this process policy here ready for us. And the next step would be to allocate this policy to all of our self-play games. So we first of all have to also add the self-play games here to our MCTS search as an argument. And let's also add them here because of that. And yeah, now we can work with them. So here we basically want to loop over all of our self-play games. So I will just write for I, then SPG in enumerate, and then self-play games like this. And yeah, inside of each self-play game, we first of all want to get the valid moves. And we can get the valid moves from the state for the given self-play game, right? And we get this state by looking at the states at the position of I right here, since this is the index we get when we enumerate through our self-play games. And this is also the same index as the one we have when we basically stack all of our states up together, right? So we can just call it like this. So now first of all we get our valid moves, and then we multiply the policy with it, but we don't want to multiply all of the policy with it, but rather just the policy at our position, right? So let's also find the policy for the self-play game. So let's just write spg.policy like this. And this should be also equal to the policy at the position of I. So now we can multiply this spg policy with our valid moves. And then again, we also want to divide this spg policy with its own sum, so that we at the end have this distribution of percentages, right? Okay, so now we create this root right here. And first of all, we should also give the states at the position I here for the state. And then also we have to make sure that this root will be equal to spg.root, right? Because we want to store it inside of this class right here. Okay, so now we have this spg.root, and we can also expand it. So let's write spg.root.expand like this. And then we will expand it with the self-play game policy we have here. Okay, so yeah, this way we already have saved a lot of calling our model, right? Because we batch up all of our states here. So this is great. And now we also want to keep doing this inside of our actual iterations, right? So here, when we basically have our num searches, we also want to loop over our self-play games again. So let's again write for I, and then SPG in enumerate SP games like this. And yeah, then we can continue with this part right here. So for each self-play game, first of all, we want to get the node, and we get this node by calling spg.root right here. And then we can just continue with these things right here. And yeah, so now here we would call our model again, right? And we want to basically, also parallelize this model call right here. So the way we can do this is by turning this if statement around. So instead of checking whether we haven't reached a terminal node, we want to check whether we have reached, in fact, a terminal node. So if is terminal. And in this case, we will backpropagate directly. So I will just copy this over right here. And in all other cases, we want to store the node that we have reached here inside of the search, inside of our SPG class as well, right? So else we can just write spg.node should equal this node right here. And to make sure that we always start with node being 1, so that we can later differentiate between the self-play games in which we have reached a terminal node and in which, or the self-play games that are that we want to expand on here later on, we also have to say that spg.node should be equal to none, like this. So yeah, because of that, we can just move that out of this loop right here. And you know what? I believe we also don't need this enumerate loop, so let's just remove that. So it's a bit easier to read it this way. Okay, so now we basically have stored all of our expandable nodes inside of our SPG classes. So first of all, we now want to find out which self-play games are expandable or not. So let's write expandable SPGs. Or let's write self-play games like this. And here we want to have the list. And then we want to store the mapping index. So basically the index we can later use when we allocate this policy and this value back to our list of self-play games. So we want to get the index basically for each self-play game, so for each SPG where our node is expandable right here, right? So we can just write mapping index for mapping index, then in range of len SPG or self-play games like this. And then we only want to get the index for all of our self-play games where self-play game.node is not equal to none, right? Since these will be the self-play games that are expandable. So if sp games of mapping index dot node then is not none like this. So yeah, this way we get the indices for all of our expandable self-play games. And next we can check whether there are even any expandable games. So you can just write if len of expand for the sp games is larger than 0. And in this case, we again want to basically stack up all of our states and then also get these encoded states right here, so that we can then get this policy and this value. So first of all, we can write states that set that equal to np.stack again of, and here we can just write spg.node.state for SPG in SP games like this. And then, oh sorry, for, no, again we have to change this up a bit, sorry. Rather we have to write SP games of I believe, or just mapping index like this, if we want to reference this one again here. So self-play games of mapping index.node.state for mapping index, and then in these expandable SP games right here. So in expandable SP games like this. Okay, so this way, first of all, we get this list of the state for the nodes that are expandable. Basically for all of our self-play games that we can expand right here, right? So okay, now we have these states right here, and we also want to encode them, but we can just move over to this part again. So I will just copy this over right here. So now again we get this policy and this value back. And inside here, first of all, we can use these expandable or these states right here. And then we also don't have to unsqueeze again because we already have a batch. Then here we don't have to squeeze again because we want to keep this batch as it is. Okay, so yeah, now we don't have to add a noise right here. So now we can again loop over our expandable SPGs essentially, right? So we don't have to do this inside of this if statement, but you could. I mean, not really changing much here. So now we want to first of all have the index that we can get our policy at the given position, and then we also want to have this mapping index so that we can then allocate this policy at index I to the self-play game at index mapping index, if that makes sense. Because the index here when we enumerate is not aligned with the index of our self-play games, right? Because we only loop for over a selected number of self-play games, right? So for I and the mapping index in enumerate, then we want to again enumerate over our expandable SP games like this. And then here we can just basically get these valid moves and this policy, and then we want to expand and backpropagate here. So let's just remove that line right here. So this is great. And now, first of all, we again want to get the SPG policy and the SPG value. So let's get SPG policy by getting the policy at the position of I. And the SPG value should also be the value at the position of I. So let's call this right here. Okay, so now we have our SPG policy and our SPG value. So now we're going to want to get these valid moves, and we get these valid moves by, first of all, getting the state of our node for the given self-play game. And here we want to use this mapping index, right? So here we can just call it self-play games at the position of mapping index. And then here we want to get the node and the state right here. You know what, let's also just, I think just store this into a variable. I think this is nicer. So I just write node equals self-play games at the position of mapping index.node. And here we just want to use node.state when we get these valid moves right here. And then here we can multiply the SPG policy with the valid moves at the state of our node. And then again, we want to divide it by its own sum, like this. So now we can get the item of our value. I think this doesn't do a big difference here. Because this already is a number array, so I believe we don't need this actually. So now, first of all, we want to expand our node using this SPG policy right here. And then also we want to backpropagate here, so I would just copy this over here. Oh, sorry. Copy this over from here. And we want to backpropagate using spg.value. Okay, so this is great. So basically, yeah, with this implementation, we have the Monte Carlo tree search code working for this number of parallel games. Now at the end, we would get these action props right here. But I believe this is not that helpful inside of our MCTS class, because here we have our we have this parallelized, and this is hard to parallelize these action props right here. So rather I would just copy this out. And instead we want to work with our action props inside of our self-play method here. So I would just paste this over to this part here. So because of that, we also don't get any action props as return here, but we just change these self-play games that we passed on here, right? Okay, so this is great. And now let's also just run this so to make sure that we don't have any direct errors. Okay, so torch is not defined, but this is just because I haven't run the sets above. So let's just quickly do that here. So let's check whether we got any error. Okay, so this is working for now. Okay, so now we want to update this part here below, and then we are finished with this parallel implementation. So after we have done this parallelized MCTS search, we again want to loop over all of our self-play games, right? So we can just write for I in range of len of SP games. And here remember that we want to remove the self-play games from our list if they are terminal, right? And it's a bit, it's quite bad to remove a self-play game from a list and then keep iterating over it from basically 0 to the len, because then we would basically not have a perfect alignment between this index here and the actual self-play game we want to reach if we mutate our list inside of our loop, right? So we can fix this by flipping this range here around. Okay, so now we want to loop over this flipped range of our self-play games, right? And then we can just tab all of these things in right here. And the first thing we want to do is that we actually want to get this self-play game at the given position. So let's just write spg equals self-play games at the position of I. And then when we get our action props here, we don't want to loop over the root.children directly, but rather spg.root.children like this. So this should be working. And so then we have these action props right here. And we don't want to add this just to the general memory, but rather to the memory of our self-play game as well. And we don't want this, when we call the neutral state, we can just either reference this one or just the state of the root node for our self-play games. Let's just write spg.root.state like this to get this neutral state. And then we have these action props here. This should be working fine. And then we have this player right here. So then we also get these temperature action props, and we get this action right here. So this are working well. And now we want to update the state. And here we again want to call spg.state, so that we update the state inside of our spg class. And we want to update this by, first of all, having the old state, so spg.state right here. And then by just having this action right here and having this play right here. So I think this is also fine. And now we get this value and is terminal by self.game.getValue in terminal. And again, we have to call spg.state inside of here. And now we check whether is terminal is true. So here we don't need to define this return memory like I said, but rather when we loop over our memory, first of all we have to set this to spg.memory. Then we want to append this to this general return memory that we have defined up here, right? So then we can just delete this return part right here. And yeah, so this is something that we have finished inside here. And then we want to flip the player after we have looped over all of our self-play games. And at the end, we just want to return this return memory up here above. Oh, and also I just noticed that when we are finished right here with this self-play game, so if our self-play game is terminal, then we also want to delete it from our list of self-play games, right? So that this while loop here is working. So here we can just write del and then sp games at the position of I. So yeah, this way we just shorten our self-play games list. And because we loop in this other direction, it will still work to just keep looping instead of our for loop. Because we will basically just remove the self-play game at this side when we loop in this direction, right? And we also have to change this MCTS to MCTS.Parallel here, right? Oh, and I also noticed that we have this error right here where we return these action props. So obviously we want to remove that line right here because we just want to return the return memory, and this statement was still part of the Monte Carlo tree search that we removed. So let's just run this again, and now we can try to train our model for ConnectFour using this parallelized AlphaZero implementation. Let's write AlphaZero parallel instead of here. And yeah, everything else can just stay the same. And I believe now the speed should be up by about 5x, so this should be a massive improvement. So let's just run this cell again, and we get this nice progress bar. So I will just train this for these 8 iterations here. And yeah, this will still take a few hours on my machine, but after that we will have this great model that has a very good understanding of how to play the game of ConnectFour. And then we can first of all evaluate it again and maybe also play against it in this nice visual way. And maybe we will lose against it, so we'll see. Okay, so now I've trained a neural network using this AlphaZero parallel class for 8 iterations right here. On the game of ConnectFour. So this still took a few hours. I believe we could have been even faster if we would have further increased this number of parallel games here, but still that's fine. So now we want to test this here inside of our evaluation cell. So first of all, let's change the path for our weights to model 7 ConnectFour, right? Since we trained for 8 iterations. And then next we can also set number of searches to 600 here as well. So yeah, we copy this value from the arguments above. And yeah, this is still quite a small number when you would compare to other search algorithms that I use in practice. So let's still check whether we get nice results here. So let's run the cell. And oh, sorry, I've accidentally ran this one right here. So let's run this cell right here. So now we get this ConnectFour board, and I believe we want to play in the middle right here. So let's see where the model plays, and the model played on top of it. I think we want to play on this side right here. Yeah, I think that should be fine. So let's play on 4 now. Yeah, the model played here. I think we either want to play here or there, or maybe there. So I will just put some pressure on the model by playing here on 5. So now I think I think we're doing fine when we play here. We just have to be careful. So let's play on 4. So now we could also pressure here, and then our model can't play here, right? Because then we could defend this. So I think probably we want to play here. So 5 again. Sorry, I'm very bad at this. Yeah, probably would have been much better, I guess, to play here then.
So now we can't play here anymore. We could still play here or there. I think this is valuable here. So let's move on top of this position here. So let's play 3. So model played here. We want to get, we have some pressure here, so maybe we'd like to play here. We also defend here, so let's play on 2, I guess. Oh no, then if we play here, our model would play here and we would be trapped. So we can't play here as well anymore. So maybe we could play here, but that's not that good either. Maybe that's fine here. It's not too valuable. So I guess we play here. Okay, so where did the model play? So it just played here. Okay, so I think we have to definitely play here. I don't know if we still lose then. So let's play on 5 now. Okay, so where did the model play now? There's some pressure here, or we lost this way, and we also lost this way. Okay, we got absolutely destroyed. Yeah, I don't know. We have to just play on 3 now, I guess. And yeah, the model took this right here, and yeah, has won the game because of that. So nice. I could have even played here as well. So that should be, yeah, just, I mean, I played quite in a bad way, I guess, but still was super nice. So now we could see that even though we have around 600 searches, our model was still able to at least destroy me here in this game. So this is fun. And before we conclude with this tutorial here, there's still some minor mistakes I noticed. So first of all, when we get these temperature action props in AlphaZero tweaks, we currently aren't using them for our probabilities. So let's change that right here. So now let's use them here. And then also when we use our optimizer, we rather wanna call self.optimizer, because then we go for this optimizer here instead of just calling this optimizer, right, which might not work on all occasions. Yeah, so that's just a small thing. Let's also add that to this AlphaZero parallel. So temperature action props here, and then self.optimizer in our training method. Okay, so now we can just lastly let our model play with itself, and let's also get this nicer form of visualization compared to just printing out this board state right here. So yeah, this is what we will do next. And here I want to use the Kaggle environments package. So I will just write import Kaggle environments right here. And then, let's also print out the version. So maybe you're interested in that. Like this. So yeah, that's my version right here. And then using this package, we can first of all create an environment. And we get this by setting env equal to Kaggle environments .make, and then here we can just use connectx to get this standard ConnectFour environment. I mean, this is also tweakable, but here we just get the standard ConnectFour environment. And then next we would want to have some players, so this should just be a list of our agents. And then next we could just say env.run using these players we have defined, and then env.render with mode being equal to IPython inside of our Jupyter notebook here. So now we also want to define our players, right? So here I've just created this Kaggle agent class, and I've copied it over right here. So basically we just do some pre-processing with the state, and then we will just call our MCTS search either, or just get a prediction straight up from our model depending on our arguments. So basically doing something similar than what we do up here in this loop, right? Okay, so yeah, now we want to create these players as Kaggle agents. And before we do that, we also need this model, this game, and these arguments right here. So we just copy them over from here, basically. like this. And then let's paste them here. So first of all, we have our game of ConnectFour. Then we don't need a player here. Then we also have to add some arguments right here. So first of all, we want to set search to true. And then we also need a temperature. And the way this is built up here, when we have temperature equal to 0, we don't do this division to get our updated policy, but rather we will just get the argmax directly. So let's just set temperature to 0 right here, so that we always get the argmax of our policy. And the MCTS distribution guided by our model. Okay, so now we have these right here. Let's also set Dirichlet epsilon to 1 so that we still have some randomness here. And so next we have our device right here. We create our model like this. And we use this path right here, so this should be fine. So now we can actually define our players. So let's set player 1 equal to Kegel agent. And like I said, we first of all need this model, this game, and these arguments. So let's write model, game, and args just like this. Let's also do the same thing for player 2. So this way we have more flexibility if we would want to try different players. And then here for the players, we can just fill this list with, first of all, setting player1.run and then player2.run like this. Okay, so this should be working now. Let's just run the cell and get these nice visualizations. Oh, so now we get this neat animation of our models playing against each other. So we have two players, but just one model here playing against itself, basically. And I believe this should come to a draw. Yeah, so our model is that advanced, I guess, that it can defend against all attacks. So I mean, this is still just this nice animation. And now we can also just briefly do the same for TicTacToe as well. So here we just have to change some small things. So first of all, we have to set the game to TicTacToe. And then also, we can change our arguments. So let's just set number of searches to 100. And here, for our ResNet, we can set the number of res blocks to 4 and the hidden dim to 64, I guess. And then we want to update this path. So I think the last TicTacToe model we trained was model2.pt, if I'm not mistaken. So then also here we have to set this to TicTacToe as well. And then we can just run this. Okay, so now we get this nice animation immediately of our models playing against each other. And again, we have gotten a draw because the model is able to defend all possible attacks. So this is still very nice. So feel free to do some further experiments your own. So maybe you could also set the search to false so that just your neural networks directly will play against each other without doing these 100 searches in this case. And so I think we're finished with this tutorial. This was a lot of fun. And I've created this GitHub repository where there's a Jupyter notebook stored for each checkpoint. And then also I have this weights folder where we have the last model for TicTacToe and the last model for ConnectFour that we have trained. And if there are any questions, feel free to ask them either in the comments or just by sending an email, for example. And I might do a follow-up video on μ0 since I've also built that algorithm from scratch. So if you're interested in that, would be nice to let me know. So thank you.